Ma'am, I think we can start.
Yes, sir. So, a very good afternoon to one and all. So, today's session 11. I am Dr. Ekta Sarda, Assistant Professor, Department of Computer Science and Engineering, IIT, affiliated to D.Y. Patil Deemed to be University, Navi Mumbai. Welcome to you all for AICT sponsored 1 week online ATAL FDP on Geo Innovations in AI for Improved Spatial Data Processing. Approved by AICTE, RIT continues to foster academic excellence and technological advancement and has come up with another program to enhance the skills for the faculty in the upcoming area of GeoAI. Now to this, I feel privileged to extend my warm welcome to such an inspiring personality, Dr. Arun PV sir. So Dr. Arun sir is currently as an assistant professor at Triple IIT Chittor. He has more than 12 years of teaching and research experience. He is also the IT coordinator of the institute. His research area includes drone and satellite remote sensing, deep learning, explainable AI, geospatial technology, and reinforcement learning. Before joining Triple IT, he worked as a research scientist and associate vice president at the R&D division, Huawei Technologies. He completed his PhD from IIT Bombay and postdoctoral from Groningen University of the Negev, Israel. He was awarded the Outstanding Postdoctoral Fellowship and PhD Sandwich Fellowship by the Higher Education Council. He was also awarded fellowships by the Italian Institute of Technology, Italy, Union of Oil Finland, Rolls-Royce Lab, Singapore, etc. He also published over 70 publications in reputed international journals and conferences. He is also the principal investigator of projects from different national agencies, including ISRO, DST, and Indian Army. He was given special appreciations by the Indian Army for his contribution towards the project this year. He serves as reviewer for many reputed journals and technical committee members from the various conferences. I welcome you, sir. Now I am requesting you to Dr. Arun, sir, to start the session on deep learning and neural networks in geospatial data. So over to you, sir.
Thank you so much, ma'am, for very kind introduction. And thank you, Dr. Prakash and Dr. Sangeeta, for the kind invitation. I am really thankful for this opportunity and really happy to interact with you all. So with no more delay, I'll share the presentation. I hope it is clear and I'm audible.
Yes, sir.
Screen is also visible, right? Okay. Okay, so here I'll be covering a brief about how these advancements in AI are being used for spatial data processing. So first I'll just have a background and then cover a little bit of ML basics, but I think already it is being covered. So I'll just have a glance of all these things, and then we will move on to some of the core research problems that I will be discussing related to spatial super resolution, spectral super resolution, multimodal data fusion. So that's overall flow of this talk. So to start with, all of us now know that what is remote sensing, how are we acquiring. See, spatial data means there are different types of spatial data. One source is this satellite remote sensing. I hope all of you are well aware of the cycle involved. Like we are when in passive remote sensing, we are using the reflected rays from the sun and get those images, same like your eyes are able to see the screen. So same way, I mean, your eyes are doing remote sensing. So same way, the cameras also will sense this reflected rays, and they are converted into images. So we have different sources of data. When we talk about remote sensing, we not only that we have satellite sources, but also we have other sources. You can carry a spectroradiometer, you can go to the ground, you can have different sources of data. You can use drones, you can use other airborne platforms for collecting the data. So that's it. So basically, this is a remote sensing image. So if you zoom in, you can see the pixels. So the pixels are the smallest pixel elements in an image. So that means we cannot go beyond that. So this is something that limit our interpretation. You can zoom in an image until a pixel. So there comes the concept of spatial resolution in remote sensing. Spatial resolution means that if I say a satellite image is having a spatial resolution of 30 square meter, it means that 30 square meter area on the ground is covered by 1 pixel. So that means this pixel value, 1 pixel value, will correspond to the energy from this 30 square meter. So as I have more finer resolution, you can see that same 30 square meter area will be now covered by more and more pixels. So that means a tree covering 30 square, or if there are multiple materials like a tree and a road and a water body within that 30 square meter area, in our earlier resolution, everything will be, if the spatial resolution is coarse, everything will be covered by 1 pixel. But as the resolution increases, or as the resolution becomes more fine, so we can see that we will have more and more pixels representing this. For example, in this pixel, you can see here roads are there, vegetation is there, everything will be represented by 1 pixel. But here, that same area will be represented by more pixels. So spatially, it became more resolvable. So this is spatial resolution. So as you have more finer resolution, more pixels will be used to represent that area on the ground. So that said, this is an example. So the same area, you can see that now nothing is visible. So as the spatial resolution increases, that means as we have more and more pixels for representing that area, so you can see that it's becoming more clear, making more sense. So we can say that a finer spatial resolution is important when we want to make planimetric measurements, or when we want to exactly detect the objects. And there is another part of resolution which is called spectral resolution. So in a satellite image, we have a spatial dimension as well as a spectral dimension. Spectral dimension means right now you are seeing this screen using red and blue wavelengths of the spectrum. But so that means our human eyes are sensitive only to the visible region, which is red, blue. So when we consider the satellite sensors, they have more capabilities. They can sense other ranges of the spectra as well. In that sense, we can have multiple other portions of the spectra. So that means you can have more and more spectral bands. In usual RGB images, we have 3 bands, that is red, green, and blue. But you can have more bands, more spectral bands. So, and you can have continuous bands. Like you can split that wavelength range. If you consider wavelength ranges, you can split it into smaller bands. So that said, if it is a panchromatic image, that entire band is covered by only a single image. So here you have 4 images covering that same area. So 4 overlapping images. One is sensitive to blue, another is sensitive to green, another one is sensitive to red, and the other one to NIR. So when I say sensitive means if you are wearing a blue t-shirt, the first camera will only sense that blue t-shirt area as white, and all the other areas will be dark. And as the blueness in that image increases, the brightness keeps on increasing. So you have, say, here 4 images. One is a blue image, green image, red image, and an NIR image. So overlapping 4 images. But in the first, in panchromatic case, you have only 1 image. And when you consider hyperspectral data, you have 200 such overlapping images. So far we discussed about pixels, we discussed about spatial resolution, then we came about, we just had a brief about spectral resolution. Here you can see this graph. This is not 1 pixel. So 1 pixel value here, since it is having only 1 band, 1 pixel will be having only 1 value. Here 1 pixel will be having 4 values. Here 1 pixel will be a vector of 200 values. Even you can plot it as a graph. That means here it will be the bands or wavelength, and here it will be the reflectance. So this is this continuous graph will tell us more detail about what object is here. So you can see here, if suppose let us take a simple example, if you have wheat and barley in a field, so each of these pixels will be denoting say wheat or barley. So for example, for this pixel, if it is wheat, and same way another pixel is having barley, when you compare that, we may not get changes. Here also same may be the case, but there will be some portion of the spectra where wheat and barley are behaving differently. That is where the spectral resolution is desirable. So we have two things, the spatial as well as the spectral resolution. So this is a brief about the remote sensing with respect to the talk that we are going to have. So the basic idea is that we have remote sensing image. That's one of the spatial data that we are using. But it's important to remember that we have a lot of other spatial data sources. In fact, we have vector data as well. Here we are more discussing about the raster data, and that too, one type of raster data, which is a satellite image, or even it's applicable for drone acquired images and other images. So anyway, machine learning, usually all of us now know, I know all of you are having expertise in machine learning, many of you. So basically we give earlier, the idea was that you give a data and you give model to the computer. For example, in GIS or geospatial spatial data analytics, usually we have a model, a physics-based model or a model on how things will work. We can give the data, so based on the model, computer will give the output. That was the earlier way of doing it. Now with the advent of machine learning, you are giving data and output. I mean, you are giving data as well as the expected output, and you are asking the machine to learn the model. So machine is learning the model, the data. So what really the machine is learning? So machine is actually learning a mapping between, this is your primary data, these are the features extracted from that data, and this is the required output. So it is learning a mapping between the data represented in the feature space, or the features of the data is being mapped to the desired output. So this is something which the machine is learning. Feature space, easily you can imagine, when we were kids, we were being taught what is an apple, what is not an apple. So someone will give you an apple, say that this is apple. So how you are perceiving an apple? You are perceiving an apple based on the color, the size, the shape. All these are the features of that. You are perceiving an apple based on these features. So same way, your machine will be perceiving this data based on this set of features which are being mapped into the desired output. So handcrafted data means actually basically you can the data that whatever you require. So for example, here it's a color and weight are the features which are being used to represent this set of fruits. So you can see that the color or the redness and the weight. So this is a feature representation. This is the actual representation of those fruits, and these are the feature representation. So we have to keep in mind that our machine learning algorithms usually work in this feature space. So it will be seeing the data like this. So it's a scatter plot where all the features are there. Each axis is a feature. So this is one feature, this is one feature. So if smell also you are taking as another feature, it will come on another axis. So image space versus feature space, you have images, but each of the pixel you can plot it in terms of the band values, the values that's having in of these bands. So if it is 3-band image, you have a if it is a 2-band image, you have a two-dimensional scatter plot. If it's a 3-band image, you can have a 3-dimensional scatter plot. So same way, if it's a 200-band image, you have a 200-dimensional scatter plot, which we can treat as the feature space. So this is something how, these are the two images, but when we are plotting it in feature space, it may appear like this, provided that these dots are the pixels. So this is one pixel, it's having this value in feature 2 and this value in feature 1. So same way you can plot any feature. So there are a lot of machine learning algorithms, unsupervised and supervised machine learning algorithms. Also there is a set of self-supervised machine learning algorithms. This is a conventional classification, supervised and unsupervised algorithms. Clustering, all of us know that we, without much prior knowledge, you can group things into different groups. So for example, if you are giving a kid a set of fruits, so based on the color, he or she may cluster it into oranges and non-oranges, and so that's a cluster. So the moment we understand that there are some oranges which are when green, so then there is a chance that the kit may make mistakes. So clustering is not always perfect. So some prior information may be required in such cases. So that's where we use classification algorithms. In classification algorithms, the kid is presented with both positive and negative samples of apple. So same way here, your machine learning algorithm is being presented with positive and negative samples of these classes. For example, I'll give some samples of water body. I'll pick up some pixels which I already know are water body, and I'll pick some samples which already I know that they are vegetation. So I'll teach the algorithm using that ground truth, and that is where it will be able to classify it properly. So this is the case when you have a hyperspectral image. One pixel will, I already told you, it will be a vector of values, so that you can give to a classifier and it will predict the label. Label means water body can be one label, the vegetation can be another label. So based on your required, I mean your problem at hand, we can classify things into different groups or classes. So this is a very toy example of how a neural network works. This is one type of a classifier. So you are presenting the input layer with the features. The features here are, this, for example, if it's a hyperspectral image, the features here are these spectral values for that. So if it is wheat will be having that wheat in that particular area will be having a particular spectral response against different bands. So that is being fed this neural network. Then what happens? It will, based on that weights, learnable weights, it will predict something. So you have two things: a predicted value, and you also have a ground truth, which is, you already know what was the expected label. So there is an error between both, and that will be back propagated, and the weights will be updated accordingly. So that is how, with the help of these weights, your neural network will learn how to transform this set of features into the output. So same thing, another way of visualizing it, you can see that first its initial random weights. So the decision surface somewhere here. So slowly you can see the machine is learning the decision surface, so that it can classify or group things on one side and other classes on the other side. So same way we can also extend these concepts to regression. So basically the idea is that, this machine learning, you have the input, for example the apple, and you have the features, which are the weights, the color, the shape, etc. You are giving it a classifier for classifying it for your desired problem at your hand. But usually nowadays we are hearing more about deep learning. Basically, deep learning means that instead of you extracting the features, you are asking the network to extract the features, or the model to extract the features. So the model not only classifies or maps the features to not only maps the features to output, but also learns the feature representation to map the feature to map them to output more effectively. So this is the actual feature. Like you can see, if it's an image with two bands, it's having band 1 and band 2. But the learned features, the feature 1 and feature 2, will have a better way, more separability or advantages over the actual set of features. So you have traditional machine learning models where you have to select the features, or you have to engineer the features and give it to the model. Here, automatically the model will be learning. This is a basic concept about deep learning. So you can see that the initial layers will be extracting the features, and you will have some final layers which will act as a classifier. So even you have some sort of so what actually we are doing here we are a lot of layers. So this feature representation will be encoded into features, which are then fed to the classifier, which is predicting the label. So you have this features are given to the network, then you have the output layer or a fully connected layer to classify it. So these are actually the features, and here we can have a fully connected classifier for classifying. So you have multiple layers, which are actually the features, and then the features are flattened and given to a fully connected network for classifying it. So deep learning are having many advantages, because most of the state-of-the-art approaches, if you see, they are deep learning approaches, basically because they can engineer better features than we engineer. Better than the user, they can engineer features based on the data. So data is being considered for finding a representation. So, but we have too many hyperparameters. So this is one of the problem that we face, and you need a lot of training data. So that may also may not always solution. So some solutions are like you can augment data, you can generate synthetic samples, but overfitting is always a possibility. So that is where you can use clustering type of approaches. But rather than using clustering in your traditional way, we can also use clustering or classification already we all of us have experimented the concepts of or learned the concepts of autoencoders. Autoencoders are nothing but you are encoding the input into a hidden representation and then you are decoding it back again the same input. So that way you are learning some hidden representations, and that hidden representations, for example, if that actual image is a hyperspectral image of 200 bands, you may be learning a hidden representation of maybe 10 dimensions. So you have a 10 band image now instead of your actual 200 band image, and you can better use that 10 band image for classification. So these learned features can be classified by any classifier. So you have an encoder, you have a decoder, the actual input from the features, and you are giving here the features to the encoder. And once this encoding is done, you can again pass this, you can get the encoded representation and you can classify it using a classifier. That's a idea. You can use any classifier for that purpose. And now one of the main problem with all these deep learning models is that you don't know what features being learned. For example, you are giving here the spectra. For example, if we take the case of a classifier, we have seen the neural network based classifiers. So here it is classifying it into different mineral groups, but we don't know what feature it is giving importance to. But as a human being with some prior knowledge, we know that okay, there are certain bands or certain spectra, certain areas of the spectra where the model should actually give importance to. Then only we can say that it's correctly learning the features. Okay. I'll just tell you a simple example to clarify it. If I have a model, I'm training that deep learning model. I'm training that model to detect cats and dogs. So I have cat images, I have dog images. I am training it with cat images as well as dog images. Okay. Now, if if my training data, all the cats are white and the dogs are black. So if I'm providing, so the training is done, everything is done. I have used white cats and black dogs. Now I'm giving a black cat. So there is high chance that my model will, a black cat I'm giving, it will identify it as a dog. So that is where, so why it is so? Because the model is considering color as a feature, as a relevant feature. So same way, when you are classifying a spectra, the model may consider some, so these dotted lines denote the actual features. And these red ones denote the features that the model is giving importance to. So you can see there is some overlapping, but there are certain features. For example, this feature is, for kaolinite, this is a mineral. This is one of the significant feature. But our model is not giving importance to these features. So same, you can compare with the cat and dog analogy. So this makes most of the deep learning models unreliable. Like you don't know what the model is learning. It may work for your set of data, but it may not work for other set of data. So these are some of the the basics, the background that I wanted to just brush up before discussing the actual problems at hand. So I hope so you can use different approaches for explaining your model. So these are some of the aspects of. Okay, so before going ahead, I hope although I'm brushing because it's basically a brush up of the concepts. So I hope I'm audible and clear.
Yes, sir, you are audible, sir.
Yeah, okay. So I understand that this is very monotonic, one-way type of discussion. Uh, because if it has been a physical talk, it would have been more beneficial. But please feel free to stop and interact with me if I'm not making sense at any point. So right now we discussed about remote sensing images and also what the basic concepts of remote sensing. We also discussed about what are machine learning, how deep learning works, what are the different uh, concepts involved. So now my problem here is already we discussed about spatial and spectral resolution. So you may recall that spatial resolution means if I say 30 square meter on the ground, so that entire 30 square meter area will be covered by one pixel. So whatever energy coming from that 30 square meter will be treated as one pixel. So if it is a hyperspectral image having 200 bands, all the 200 band values are coming from that 30 square meter. Now, if I decrease the swath, or if I decrease the instantaneous field of view, that means that area of that square. Earlier it was 30 square meter. Now, if suppose I am using a 5 square meter, so the energy coming from that 5 square meter has to be represented in 200 bands. So that means that the earlier the energy from 30 square meter, I was splitting that energy into 200 bands. Now that 5 square meter, the energy coming from that 5 square meter area is being split into 200 bands. I hope now it's making sense, because as you increase the spatial resolution, as you make spatial resolution more and more fine, so the area or the instantaneous field of view decreases. So that means 30 square meter means it's a coarse resolution, coarse spatial resolution. 5 square meter means it's a fine spatial resolution. So in order to get a finer spatial resolution, you have to focus on smaller area. So the energy coming from that smaller area is very less. So you will not be able to split it into different bands. So what happened? There is a trade-off between spatial and spectral resolution. So that means if you need finer spatial resolution, you will suffer, you will have coarser spectral resolution, because the energy coming finer spatial resolution means you have to focus on a smaller area, and the energy coming from that area is very small. So that means you will not be able to split it into different bands. So this is a problem. So when you have high spatial resolution, you have low spectral resolution. When you have high spectral resolution, you will have low spatial resolution. So this is a trade-off. So that said, so panchromatic images will have a high spatial resolution but a low spectral resolution. Same way, multispectral image will have medium spatial resolution and medium spectral resolution. Hyperspectral images will have high spatial resolution, high spectral resolution and low spatial resolution. So this is a problem. So how we can solve this problem? So that is, the solution is that one is that you lower the altitude, but this is not, a practical solution. So a feasible approach is to spatially enhance the hyperspectral image, or spectrally enhance the multispectral image, or fuse them both. So if suppose you have a high spatial resolution image and a high spectral resolution image of the same area, that means you have a panchromatic image and you have a hyperspectral image of the same area, you can fuse them together. There are different approaches for fusing them, but this is difficult, so you need to have both the sensors covering the same area. So this is not always possible, because you can see most of the satellite are having one sensor, and that will work independent of other sensors. So the problem here is, so you have now if you have hyperspectral sensor, so the solution is that you enhance the spatial resolution of hyperspectral image, because hyperspectral image is having high spectral resolution but a coarse spatial resolution. You try to enhance it spatially, or other way around is you spectrally enhance the multispectral image. So when I say that you spatially enhance the hyperspectral image, what does it mean? It means one pixel in hyperspectral image correspond to 30 square meter, provided the resolution of this hyperspectral image is 30 meter. You are saying that this 30 square meter area being represented by one pixel, you have to go beyond that. Yeah. Okay. So that means your pixel is covering 30 square meter area, right? So the problem is now how you can go beyond a pixel. I already told you pixel is the smallest element of your image, but our solution says that you have to go beyond pixel. So that means you have to break the pixel. You have to even understand what is within that pixel. I hope all of you got the problem. So you have a 30 square meter area. In your hyperspectral image, this 30 square meter area is represented by one pixel. Now, if I want to increase the spatial resolution, say 5 meter, I have to split this 30 square meter area into multiple pixels of 5 square meter area. So that is something which we have to do, and we have to do it with the help of machine learning. I mean, there are different approaches, but one viable approach is to use machine learning because we can use some sort of a. So mixed pixels basically means that if I already told you in one image that one pixel is covering road, and it also has soil, it also has vegetation. So you can see that multiple constituents are mixing in that pixel. So I'll get one response for all these objects or all these components. So I can say that the spectra that I'm getting is a spectra which is mixed of the pure spectra of soil, the pure spectra of vegetation, and the pure spectra of water body. So all these spectra are mixed together to give me the spectra of that particular pixel. But the other case is when one pixel is covered by one material only. So if only soil in that area, so the response I'm getting is a pure response. It's a response of the soil. So these are some of the problems that we will be trying to address in this talk. So these are some of the benchmark data sets that are commonly available if any of you want to experiment with any of these approaches. These are all hyperspectral data sets. For example, you can see Selena's data set. It's an average data set. So you can see that this is having like almost around 204 spectral bands. So each pixel will have 204 values. So we have to always remember in the case of RGB images, one pixel will have only 3 values. But here one pixel will have 204 values. And this image that you can see here is the ground truth for this image. This is actual data. This is the ground truth for that data. That means this area saying that it corresponds to this particular class. That means this class vineyard. So now again, so same way you have different ground truth labels for different classes. So you can use them for training your model. This is another famous Indian Pines data set. So you can see that here also we have labels. Then you have Pavia University. Actually, I will not be able to see the chats since it is running in full screen. But if you can, if there are some in the chat box, please feel free to read out and interrupt me. So you have Pavia data set, KSC data. All these are available online, and even the average NG data is also downloaded. But only thing is ground truth may not be available. But you can request the agencies for ground truth. Some people may be having ground truth, so you can then request them based on the publications. I mean, if someone is using average NG data, so if they are using it on your own. So now coming to our point on spatial resolution enhancement, how are you spatially enhancing a given hyperspectral image? That is the question. That means if you get an image like this, so can you make it like more spatially clear or spatially finer image? So that is something which we are going to learn. Before that, we just have to understand the background of images. So for that, I'm just taking a very simple example of a signal. So here you can see this signal. So this signal, if I say that it is composed of all these signals, that means this signal plus this signal plus this signal plus some other signals gave this complex signal. So the concept is very clear. I'm saying that this signal is composed of all these signals. That means I took some weightage multiplied by this plus weight multiplied by this plus some weight multiplied by this gave me the signal. So in that case, I can also say that my image is a two-dimensional signal. So here you can see in a signal, the amplitude is varying with respect to time. Here amplitude is varying with respect to x and y. So if you consider any image, the amplitude, you have a pixel value there that we can consider as the amplitude. As I move x and y positions, it will change. Now I am moving in this direction, so it is changing. If I move in this direction, it will change. So same way, the change in pixel values with respect to x and y can be considered as the frequency of an image. So an image can also be expressed in terms of base images or this type of simple constituent images. Same concept, analogy with the signal. This is a complex signal. I am expressing this signal in terms of some simple base frequencies. Same way, if I have a complex image, I can express this in terms of some base frequencies. So that said, so sparse coding is a more generalized way of expressing a complex signal in terms of base signal. Here the base signal are base frequencies. If you take wavelet transform, they will be wavelets. So here I am generalizing it in a more broader sense. I am calling them as dictionaries and sparse codes. Sparse codes can be the weights and dictionaries can be the bases. So it can be a Fourier base, it can be wavelet base, or it can be any other base. So that means if I have a signal y, I can represent it in terms of bases as well as their corresponding weights. So that said, so I can express an image. Imagine that this image is, in one dimension. Image is actually a two-dimension thing, but we are just reshaping it into one dimension. And then these are the dictionaries and these are the sparse codes. So you can see that multiple base components combined together can be combined together to form each pixels. So this is the same, but you can see here many of the coefficients I can make them a 0. Why? Because if suppose we are dictionaries, or you can see here the signals, I can have infinite number of bases. So what is a better way? Better way is to restrict the number of bases. So I can reduce the number of bases. Instead of I am having say 1000 bases, I can just use maybe 10 bases. So sparse coding basically means that you want to keep the bases as bare minimum as possible. That means these are the bases. So many of these codes will be 0 and only some will be non-zero. So that means only those corresponding dictionaries will be used. So now the sparse coding, so you have this image patches, you are representing y equal to alpha. So that means y is your image, d is the dictionary, and alpha is your sparse code. Now how I can learn this dictionary sparse code? That is using this formulation. So that means we have to find d and alpha in such a way that when we multiply d with alpha, we get y. D and alpha, this matrices. This is d, this is alpha, the matrix of alphas. Okay. So d multiplied with alpha should give y. At the same time, what is the condition? The condition is that d multiplied with this alpha should give me y. At the same time, alpha's L1 norm should be minimum. That means alpha should be having more zeros, zero entries. See, L0 norm means the number of non-zero values. L1 norm is the absolute sum. L2 norm is the squared sum. So same way, it is desirable to have L0 norm, but it is not differentiable or continuous. So we are using L1 norm instead. L1 norm is also having problems. So we have to have a way around. We try to reduce the number of number of coefficients or number of sparse coefficients. We have sparse coefficients. So this is a more intuitive explanation of what we were just trying to say. You can see that these are the images. So when you take some patches, any patch of this image can be represented in terms of this learned bases. So you can see some of these bases can be, say, so I'm taking one patch. One patch can be expressed in terms of maybe this feature multiplied by some value, this feature multiplied by some value, plus this feature multiplied by some value. If you add it together, it will give you this patch. This is your actual image sample. So in other words, you have these digits. You can see here, these are the sparse codes. When you multiply them and combine them together, you will get the actual image representation. So any images, we can express them in terms of sparse codes. So basically, if you have an image, you can represent it in terms of dictionaries and sparse codes. It's a more general approach as compared to your transforms, for your wavelet or other transforms. So now we all of you are aware about the concept of convolution. You have a filter. The filter for each neighborhood, it will be taking as a weighted sum based on the filter coefficients, and those values are the values that we are getting here. For example, this 4 correspond to this particular neighborhood, this neighborhood. Okay? Now 3 correspond to the next, 4 correspond to the next, and some things like that. So now if this is the filter, if you convolve around the filter, you will get some feature. So this filter value can also be an edge detector, because it can detect the edges. If you just replace this value with an edge detector, -1, -1, -1, 0, 0, 0, 1, 1, 1, 1, then it will give you the edges. So same way, it can be anything. So this is convolution. So you have filter 1, filter 2, you convolve them to get the desired, convolve them to get the desired features. So these are maps. So you have an image, you convolve them with these filters to get the feature maps. But now your problem is how to build. So here the idea is that instead of just multiplying, we can use convolution. So this is called convolutional sparse coding. It also works the same. You have dictionaries, you have sparse codes, you are convolving the dictionaries, with sparse codes, and you are getting, you are putting the same condition here. So, but mostly in all practical implementations, you can take this as a intuitive note. The sparse codes will be the sparse codes will be the features, and your kernels will be the dictionaries. So your kernels are dictionaries, or filters are the dictionaries, and sparse codes will be the features. That means the basic intuition behind that is that when you apply filter onto an image, you can generate different features. So that means now these features are the base signal for this actual image. So that is where, this is the concept that we were just discussing. So you have dictionaries, which are the filters. You can convolve them over the features, and you can get the reconstruction. So this is called convolutional sparse coding. So the basic idea is that you convolve the dictionaries and sparse codes to get the image. Now coming back to our neural network concepts of the machine learning that we have learned. Convolutional neural network, all of you know that it's a type of neural network which is a shared weight neural network. So the basic idea is that instead of having all layers connected to all the next level layers, we have here only a few of these layers connected to, few of these neurons are connected to this neuron. So here you can see, if you see this neuron, all the lower layer neurons are connected to this neuron, but this is not a fully connected one. This is it's more like a shared weight or a sparsely connected network, which is convolutional network. So this is an actual, if you are passing an image to an actual neural network, a fully connected network, all these pixels will be connected to this. But here, only some areas are connected to one neuron. So this is called the receptive field of this neuron. So only those pixels in the receptive field, or only some features are being connected to this. Now let us see how that connection works. For example, consider this area, not the highlighted box, but you consider this area, okay? 1, 0, 0, 0, 1, 0, 0, 0, 1. Now I am using this filter. Okay? This is my filter. So I'm placing this filter over this image. So I'm placing this filter here. So that means I have 1 0 0 0 1 0 0 is my image, and my filter is this one. So I'm placing it over here. So what will be the convolutional output? Minus 1, 1 multiplied by 1 plus minus 1 multiplied by 0 plus minus 1 multiplied by 0 plus minus 1 multiplied by 0 plus 1 multiplied by 1 plus minus 1 multiplied by 0 plus this plus this plus this. Correct? So this is, the convolved output for this filter over this, give me that output. That's 3. So I should get a value 3 out of this. Now we can see if this is a neural network. I am representing this image in a one-dimensional way. That means 1 0 0 0 0 1, then 0 1 0. I am placing this here, placing the next row here. So it's a one dimension now. This image, 6 by 6 image, it's now becoming like a 1 cross 36 vector. So this is that image. Now you can see here in this image, this is connected to this one. So the first element is connected to this neuron, second element is connected to this neuron, third element is now connected to this neuron, but the fourth, fifth, sixth and seventh are not connected to this. Now I'm straight away going to the seventh. So fourth, fifth and sixth are not connected, but seventh, eighth, ninth are connected, 13, 14, 15 are connected to this one. Why? You can see here, this is the first one, this is the second one, this is the third one. So these are connected. Now fourth, fifth, sixth are not connected. Seventh is connected, eighth is connected, ninth is connected. 10, 11, 12 not connected. 13, 14, 15 are connected. 16, 17, 18 and rest are not connected. So that means now my neural network, or that neuron, that particular neuron is focusing on this area. Same way, I have now the highlighted portion. So you can see that this portion is now connected in this. So whatever value you are getting here for this neuron is the convolution of this filter over this area. Whatever value you are getting here is the convolution of this filter over this neighborhood, the highlighted neighborhood. So that means by connecting this manner, you can simulate the convolution. So that is why this type of neural networks are called shared weight or convolutional neural network. Remember that they are having shared weights. That means these weights are shared here also. I mean, weights are kept the same. So this is a whole neural network. You will have convolutions, and then once you have the features, you will again convolve it, but you will take up, only some from one neighborhood. Maybe you will take the most prominent one, and then you will try to pass it to the next level. So again, so these are actually your features, and you can now flatten it, connect it to a fully connected network, and you can do the prediction. So instead of we learning the features of a cat, now by doing this, we are making the network to learn, and finally this feature, whatever is being learned here, is the one which denote this image, and that feature will be now fed to the fully connected network. So that said, you are learning features at multiple levels. So you have edges, you may have object parts, finally the object models will be learned. So you can see here when a car is being passed, or for another model, how for different objects, different features are being getting activated. Now when we already talked about autoencoders, now same is the concept of for the convolutional counterparts also. So you have convolutional networks, you have multiple convolutions. So and you will have the hidden representation. Again, you will have a decoder, which is again having multiple convolutions, or we can say the transposed or deconvolutions, and it will generate the so for learning it's hidden representation. So this is what. So now for sparse coding based super resolution means now you have an input image, you can represent that input image in terms of the dictionaries and sparse codes. Now our idea is that you have two types of images. You have a high resolution image and a low resolution image. The core idea is that the high resolution image will be decomposed into high resolution dictionary sparse codes. And now you can learn the sparse codes from the low resolution image. So given high resolution image and corresponding low resolution image, you can learn this mapping. Now, so here you don't know alpha, you are getting that alpha from the low resolution image. So now this is your algorithm. You will train the network with simulated coarse image. Coarse image means, see, usually the ideal situation is that you have a set of coarse images and high resolution images. That means, again, you need a sensor covering, I mean, two different sensors covering the same area for that purpose. But most of the cases, this is not available. So what we are doing is that we will take a high resolution image, will scale it down, and now we will use that scaled down version as the input image and the actual image as the high resolution image. So this is, you took this high resolution image, which, for example, you take the Indian Pines data set, you downsample it or downscale it using any different types of um, scaling techniques like bilinear, bicubic, nearest neighbor, or anything. You generate this synthetic data. Now you use this data as the input to your model, and you are expecting this one. So now you have input and expected output. You can train your network for the same. So usually, I already told you, so you have this a low resolution image and you have high resolution image, super resolved image. Now we can model it in terms of sparse coding. The intuitive idea is that the filters are the dictionaries and the features are the sparse codes. With this idea, we can map a low resolution image to a super resolved image. So that means you can have a bicubic upscaled coarse hypercube. You can pass it on to the dictionary to generate the features. Then those features, which are the sparse codes, are being passed to the high resolution dictionary to get the sparse codes are being learned using sparse coding, and the backpropagation will automatically refine it to learn the dictionaries in conjunction with the learning of sparse codes. So all these blocks can be convolution blocks, multiple convolution blocks. So usually, in our researches, we started using 3D CNN because you can jointly learn both 2D, I mean, as well as spectral features. But there were a lot of issues with this because prior to our work, this sparse coding was not being modeled explicitly. So we tried explicitly in the sense that within the image itself. So for addressing these issues, we tried to develop our own sparse coding sub network, which can be embedded into a neural network layer. So the basic idea is that you get an input hypercube, you split it into different patches, you pass it through a stream where you will deconvolve it to get the feature. And now, once you have the features, so what you do is you will convert those features. I mean, you try to optimize those using sparse code optimization. Then now what you do is you pass it through a filter, a high resolution filter, to get the latent representation of those high resolution images. You invert it again using convolutional units and get back the image. So this is the basic idea. There were many modifications to this. So the basic idea here is that this is your actual algorithm that we will be using. Already you are familiar with this formulation. That means this is your sparse image, this is your sparse code, this is the dictionary, low resolution dictionary. You are making this objective, and here the objective is to learn an Z in such a way that Z, when multiplied with DLR, when convolved with DLR, should give you the YLR, which is the low resolution image, and at the same time it should be as sparse as possible. So that means you are learning the sparse codes from the low resolution image, and you are using that sparse code for projecting, and that sparse code is being projected onto the dictionaries, the high resolution dictionaries, to get the actual super resolved image. So but this particular sparse coding This we cannot embed it directly into your convolutional neural network. I cannot directly embed it. So we have reformulated it in an iterative form, and we came up with a formulation by which we can iteratively embed this sparse code generation onto this network. So hand in hand with the back propagation, automatically sparse code optimization will happen, and you will get the super resolved version. So this was implemented using, it's an iterative form, so it was implemented using a shrinkage thresholding approach and a recurrent neural network for implementing it. We have adopted a recurrent neural network for implementing. So we came up with some more approaches. Due to the time limitation, I'm not explaining it in detail, but the basic intuition is that we are trying to model the sparse coding using convolutional neural networks. So the basic idea is that we can, so this has given us, you know, a base for embedding many of these algorithms onto a convolutional neural network, because you can transform them into an iterative form, and then you can try solving this in a convolutional framework. The good thing is that here you are learning the features, so automatically that those features or those sparse codes and dictionaries are automatically being learned jointly. So these are some of the advancements where we use the different other algorithms. So our basic idea was that, we developed all these algorithms. So the basic idea was that you input coarse image, it will give you a super resolved image. Problem is that this is a deep learning model. So once you train it, it will be static. That means your trained model, you don't have an option to improve it. So if I trained it for a particular sensor or a particular type of data, it may not work very well for other set of data. So this is called generalizability. So these models lack generalizability. So what we proposed was like, okay, we are getting the output from the model, but can we further refine it? So that is where we unmixed both the both these images to get n members and abundances, and then used them to refine this initial estimate. So the intuition or the idea or the assumption is that, since both of them are covering the same scene, n members or the pure members will not change, because if there is soil there will be soil here also for this image also. If there is water body, there will be water body here also. So you can use them as n members abundances, and you are enforcing that n members to be same. So that way you can further refine this super resolved estimate with respect to the input image. So this improves the generalizability of the approach. This again, same thing that we discussed. So if you don't have actual ground truth images or multi-sensor images, you can use this type of a framework to simulate and test your algorithms. So these are some of the results on Selena's dataset, and some of the quantitative evaluation metrics like RMSE, things we have used for evaluating PSNR. So the basic idea behind all these approaches that we developed is that, usually there are a lot of super resolution approaches, but the problem with all these approaches is that they are classical approaches, or they are for usual RGB type of images where individual bands are being enhanced, but that will not work for a hyperspectral image, because the spectral fidelity is of prime importance. That means if you individually enhance each band, you may lose that spectral fidelity. Spectra that we are talking about, so a minute variation will actually change the object itself there. So that pre-processing may change the entire. So this paper has been published in IEEE Transactions on Geoscience and Remote Sensing, and some related works are also been published in CVAU, ISPRS, pattern recognition type of journals. You may please refer to this if you need more details regarding this approach. Also, please feel free to get back to me in case you have any doubts. That is one problem. Okay. So spatial super resolution, or you spatially enhance the resolution of this images. Okay. So I'll just, although I know that it's very intensive listening 1 hour. So since I have few more slides, I have some more slides, but I will not cover in detail, but I will just give you the problem and the intuitive solutions for those problems, which you can explore if you are interested. So far we were exploring something like, you have an image, you try to reconstruct a finer image or finer resolution image, finer spatial resolution image. So that means you are going beyond a pixel. You are breaking that pixel into small sub-pixels. So actually, many of the remote sensing applications do not require the full image to be reconstructed, because most of the time what you need is classification maps. You actually don't need the actual image to be reconstructed. One second. We actually don't need the complete image to be reconstructed. So we just need the the labels. So what if I'm saying that, without reconstructing the actual image, you have coarse image, you directly generate high resolution classification maps. So for that, there are two processes involved. One is spectral unmixing. That means I told you already, a pixel response, if there are multiple components there, multiple n members there, it will be, the spectral response will be mixed. So the spectra that you are receiving or you are seeing at a pixel will be a mixed spectra of soil, water body, vegetation, different things. So you can unmix them. And now, once you unmix, you know that how much percentage of soil is there, how much percentage of water is there, how much percentage of, say, vegetation. Yeah, I think there are some chat messages. I'll just go to them. As I told you, I'm not able to see them otherwise.
Probably we can end this, answer these questions towards the end of the lecture, maybe.
Yeah, that's also fine. Yeah, but anyway, since I checked it, I'll just go with it. So
Sure, sure.
one person asking, what are the important features in spatial and spectral resolution in remote sensing data? See, basically, spatial resolution means it's a characteristic of the data. Spatial resolution. Spatial resolution, if I say it's having like 200 bands and 10 nanometer bandwidth, that means I have that entire electromagnetic spectrum, which is being split it in 10 nanometer interval range. That many bands I can have. So these all are the features. Your spectral bands are your features. Okay. So spatial features means the features, you are extracting from the spatial neighborhood. For example, it can be edges, it can be corners, it can be some other features. These are spatial features. Spectral features means these are the bands, or it can also be the absorption features, the reflectance features. I have in my PPT, I have shown you one spectra and I have highlighted certain important features, right? So that means for that particular mineral, these are the portions which are important. So that's, these are the features which are important. So that is one thing. So I hope I answered your question, Sushant. Okay, thank you. Yeah, Anaka, I hope we can take up the question towards the end, if you don't mind. If it's something critical, you can even ask also.
Hello, hello.
Yeah, please go ahead. Yeah.
No, sir, no doubt. Actually, I think it was by mistake.
Fine,
Thank
no
you,
problem.
sir.
Thank you. Okay, so I'll just start discussing about the spectral unmixing part. So basically, spectral unmixing means we have to understand that we are unmixing the data. That means you will get the abundances. For example, here you can see this particular pixel. It contains both tree as well as soil. Okay? So this is like tree as well as soil. So if I take the pixel value or the spectra corresponding to this pixel, I'll get the spectra of soil mixed with the spectra of tree. So that means I have two spectra mixed together. So what will be the proportion of each spectra? how much area is being covered by tree. So that area will denote the proportion. That means if more area is covered by tree, I get more weightage for the tree spectrum. If more soil, I'll get more weightage for the soil spectrum. So that means if I assume a linear mixing, so what will happen here is the spectra of soil multiplied by the fractional area covered by soil plus spectra of tree multiplied by the fractional area of pixel. So that is what 15% soil, 25% tree, 60% grass, 3 by 3 meter pixel. So that means the spectra I'm getting will be a mixture of all these things. So 0.15 multiplied by the soil spectra plus 0.25 multiplied by tree spectra plus 0.6 multiplied by grass will give me the spectra of this area. So that means from this one value, I have to get all this information from one value. From 123, I have to get this information. From 133, I'll get this information. From 139, I'll get this information. So this is called spectral mixing. Spectral mixing means this is what is happening at acquisition time. And what we have to do is spectral unmixing. So a usual approach is that, we assume a simplex and scatter plot all these. Like if we have two bands, we have a two-dimensional scatter plot. I already discussed with you. This is a feature space. So when we see that, when we are plotting things in a feature space, if it is 2D, you will have a triangle. You can see that the corner points of the triangle will be the pure pixels. Why? Because any internal points you can express in terms of other points, but these points we cannot express them in terms of any other points. Okay? So that is the intuition that we use to detect the pure members or n members. To detect the n members, we can just formulate them. We can solve this optimization problem to get the abundances. So that is how we estimate the abundance. So this formulation is nothing, but you multiply the abundance with the n member matrix plus some error will give you the actual element y, actual image y. So that means if this is the actual image, you can have abundances for each of the classes. So spectral unmixing, and then you can also use classifiers for unmixing, because classifiers means usually you hard classify them. For example, if I have a pixel, I can label it as plant or tree or soil or grass. But at the same time, I can also soft classify it. That means I can say that 0.5 is the affinity of this model towards. I can use a softmax to soft classify. So we can also one way connect the softmax classification with unmixing, in the sense that whatever probabilities we are getting are proportional to the area being covered by that particular entity in that pixel. So fuzzy based approaches are there. So that is one way of doing it. And you can also use deep learning approaches. So the basic idea is that you have an encoder here. Encoder is encoding some values, and then you have a decoder which will decode it towards the, you will get the same input as the output. But the decoder waves, you can keep them fixed. You can make them the n member value, so that whatever hidden representation is being learned here, we are saying that this will be multiplied by this n member matrix to get your actual image. So that means automatically this hidden representation will be the abundances. So such constraints we can apply to unmix a given image. So there are different variations for these different more complicated and effective networks of doing unmixing even. Yeah. So the basic is that you have an encoder. You can force that encoder to learn the abundances, and also you can also have softmax based classifiers that can also be deep learning based classifiers. So these are two approaches that are being used in deep learning based spectral unmixing. So again, subpixel classification. Now spectral unmixing, you got how much area is being covered by each of these entities, but you are not clear about where are they. I know that this pixel contains 60% soil, but I don't know where this 60% is. So that is where subpixel classification comes into play. The assumption is that the spatial continuity. That means most of the similar things will be nearby. So that is where you try to optimize it based on the spatial continuity. That means you can see here that class A, this is a fractional abundance. This is for class B. This is for class C. That means this pixel contains 0% of class A. It contains 50% class B and 50% class C. Now, where are these here, right? So we are saying that here, since class A is not there, there is no representation here, but B is there. But B could have been here also, right? So based on the continuity, we can say that B should be here because it should be continuous with this pixel, which is also in B. And so A should be here. So that's where some spatial continuity constraints, based on that, we can optimize them. And there are different approaches in optimizing them. So why it is an optimization problem? Because given this abundance, this can also be a subpixel classification map. This can also be a subpixel classification. But here you can see things are more continuous as compared to here. So this will be a better subpixel classification map as compared to this one. So the most important thing that we have to understand is that here the fractional abundance we are getting from spectral unmixing, and then subpixel classification will help you to get the spatial distribution of these subpixel labels. This is your actual pixel, the bigger squares, and we are breaking them into smaller squares. These are all subpixels, and now we are labeling. So that means your actual coarse image is now transformed into a high resolution classification map. So we also proposed some joint way of doing spectral unmixing and subpixel mapping using deep learning based approaches. So we used a soft classifier based approach for learning the fractional abundances, and then a deconvolution based approach for having the subpixel mapping module. So we are jointly optimizing it to achieve this. So these were some of our results were promising. And now, so far we were discussing about spatial resolution enhancement. We can also discuss about spectral resolution enhancement. That means spatial resolution enhancement means you are going beyond a pixel. You are spatially breaking the pixel. Now, if I'm giving you a multispectral image, which is having a medium spatial super resolution, sorry, spatial resolution, can you increase its resolution, spectral resolution? Earlier, we were attacking the problem by improving the spatial resolution, but can we also improve the spectral resolution? For that also, we can, so given a multispectral image, can you transform it into a hyperspectral image? So for that also, we can use the approaches that we discussed. The idea is that, in spatial super resolution, you spatially resolve a patch. Now you take the pixel vector. Now you try to super resolve that pixel vector. But the only problem is here that spatial consistency will be lost. So now you use another network or another way to regain that spatial consistency. Okay, so that is where spectral super resolution approach comes into play. So you use a CNN based framework to spectrally enhance each pixel vector using the same approaches that we discussed. Then we used a 3D CNN to further refine it so that we get the, and then a joint spectral unmixing based approach was adopted that we discussed during the spatial super resolution part to super resolve the image. So these were some of the, here also, same way we'll be doing it. We'll be having a actual image, we'll be downscaling it spectrally, not spatially. We'll be spectrally downscaling. That means if you have 200 bands, you can make it 100 bands, then you will try the network to reconstruct those 200 bands. So these are some of the publications related to this. Also, we can fuse multi-sensor. Don't worry, I'm just winding up in 2 to 3 minutes. So multi-sensor data fusion. So you can have multiple sensors. Okay, so multiple sensors means our problem here is you can have like UAV patches, you can have ground measured spectra, you can have different satellite images. So if they are overlapping for some areas, we can try we can transform the multispectral data into a latent representation, and then we can also transform the the spatial data also into a latent representation, and you can map between both. So these are some of the results that we got. Also, we can use it for extracting the objects and the relations. Here, one thing I just want to highlight is that, see, right now we discussed about using multiple satellite images, drone images, all raster data. We can also
Pankaj sir, please,
I thi-
please mute.
I think we can also think about fusing vector and raster data. This will give you some idea of doing that. See, we can extract the objects and relations from this data, and you can also fuse the vector data, because vector data already is in vector forms, having relations, it's having the particular objects, the topology is there. So that way also some approaches are there. So these works were published in Information Fusion and JSTARS type of journals. Also, you nowadays you are quite aware about adversarial networks, GANs, generative networks, variational autoencoders. We can use these different types of approaches for all those applications I mentioned earlier. So basically, the most relevant part is to use them for generating data patches. I mean samples, training samples. For example, in hyperspectral data and other ways, places, getting training data is very difficult. So you may have a limited set of training data. You may have to augment and use them. So just to touch upon other applications, when we use multi-model, when we say multi-model data, sometimes text data is also very important, because for example in mineral prospectivity modeling, you have satellite images, you have a lot of reports published by Geological Survey of India and other people. Can we combine both of these modalities? That's also something which we can explore as a prior knowledge. Also, nowadays people are talking about reinforcement learning. See, the idea of reinforcement learning is more of a self-supervised learning, right? So, see, in childhood, we learn things in supervised manner. We learn things in unsupervised manner. That means, given a set of fruits based on the color, we can group them. Or if someone tell us like, okay, this is orange, this is apple, we will understand the features and we will try to classify them. So that's supervised learning. Certain things we learned also in an unsupervised manner. That means usually when someone will come to home, if we speak in a loud voice, then we may get scolded or we may get even beaten up. So we learn from positive and negative rewards how to behave properly. So that's one thing, like is a self-supervised way of learning from rewards, which is also so we also used reinforcement learning. See, where we use these, like usually deep learning models, once they're trained, it is static. So can we update the weights again based on, or can we refine them, these models, based on this type of online feedbacks, or some sort of feedback based on the generated outputs. So that's something so basically, to conclude, intelligence is required in many of the data processing applications that we covered with respect to resolution enhancement, and also we touched upon spectral resolution. Idea is that the spatial data, whether it is remote sensing data, hyperspectral data, or some other data, this has got many unique characteristics, unlike the other data. Okay? So we have to know the features and we have to select the appropriate approach. This is very important. Yeah, this is very important. I just missed it. The classical machine learning models are still useful and valid. So we have to be very intelligent in choosing. It doesn't mean that DL will work everywhere. We have to be very intelligent in choosing that. These are some of our collaborators and these are some of the projects that we are having. Any of you, if you are interested, please feel free to shoot an email and work with us. And once again, I thank you all for really had to listen in this afternoon hours, this much continuous lecture. So I really appreciate and thank you for joining. I again thank Dr. Prakash and Dr. Sangeeta and all the other organizers for the kind invite. I'm open to questions. Thank you.
Thank you so much, sir, for sharing the valuable insights with us. Now it's chance to the question and answer sessions. So dear participants, please free to fill the questions.
Hello, sir.
Hey, hi.
Hello, sir. Good
Yeah.
afternoon, sir.
Good afternoon.
Sir,
Yeah.
thank you for that wonderful presentation. Sir, I had one doubt regarding the neural network, how we can apply for the land use applications. Sir, generally, when we are doing land use applications for different time period, as you know, when we run it on a laptop, it will consume a lot of RAM. Sir, is there any method where we can optimally use neural networks for the land use application, sir?
Yeah. Yes, sir.
So
Actually, the
specifically,
problem
I'm
that
talking about the satellite data which we use. Generally, the Landsat and other satellite data when we use for land use applications. Let us say I want data for 30 years, so that makes 30 images. So how effectively we can use that, sir? Thank you, sir.
I understood your question. So basic idea is, the basic problem that all of us face is this computational complexity, because most of the deep learning models, they are very deep, and training them takes a lot of time. This is one problem with all the deep learning models. This is something which we cannot do much also. So that's one problem. But there are a lot of lightweight neural networks. Even you can refer to some of our papers in accelerating neural networks, where actually we try to prune some of these layers automatically. So one way is that you can use such modifications. Otherwise, there is something called pruning. So pruning basically means you can prune out some filters or some unwanted things at network level. So there are pruning possible at different levels. That means one is you use some modified convolutions or modified type of approaches which may not require that many number of layers. That is one thing. Other parties, you can prune these filters and other things, so the number of learnable parameters will be less. Other way around is, the feature part. So that means the input features, you are saying, like when you take the temporal data, we have 30 years of data. This is quite uh, cumbersome data that we are having, like a lot of huge amount of data. So what you can do is, see, first we can even pass it through some sort of a dimensionality reduction technique. Like for example, if it's PCA works, if you can use PCA or any other type of technique to reduce features, and then try giving those features as input to your deep learning models. Or you can also use, other type of nonlinear regression techniques also. But as I again told you, there is always a trade-off between computational efficiency and accuracy. So always this is a problem. Extent we can attack this problem, either you prune the input features, you use some other method to get other set of features. There are two types of dimensional. One is feature extraction, which is like PCA type of things will do. Otherwise, it is more like a feature selection. You can also algorithm type of approaches for feature selection. The speaker after me, Dr. Shakti Sharma, during his PhD, he has extensively used colony optimization type of algorithms for feature selection of approaches. Okay. Yeah. Okay. So I hope, Chandan, I cleared your up to some extent.
Absolutely, sir. Absolutely. I have noted down about dimensionality reduction, that is PCA. I'll
Yeah,
try to work on
PCA
it,
also,
sir.
see, PCA is a linear approach. So sometimes PCA may
Yes,
not
yes.
work, but mostly for the data sets it may work. So PCA, then you can also try other approaches. See, autoencoder based approach also you can try, but again it is computationally it is computationally very expensive. That's one problem.
Intense.
Yeah,
Intense.
yeah.
Yeah. Okay. Thank you, sir. Thank you so
No,
much.
no problem. Thank you. In,
Anyone else?
Good afternoon, sir.
good afternoon, sir. Please.
Sir, it is a very nice presentation, sir. I
Thank you.
really enjoyed the session. And I have one question regarding the platform that can be used for this geospatial AI. Could you please suggest a best combination of tools that can be used for satellite images? As Dr. Chandran said, for multi-dated images, multi-temporal images.
Platform in the sense that what exactly are you in? Is it methodology or
Software kind of thing, and
Acha, okay, okay.
also for
See,
Python.
usually I use Python plus I use this GDAL type of packages for reading this data and other things. But once you read the data, it is pretty much same. It's in metrics form, so you can use any. So in Python also now you have PyTorch, other things. So basically you can either use PyTorch, because all these PyTorch or TensorFlow, they also come up with an inherent parallelization. So the thing is that they also ease out many of your computation tasks. But if you are a beginner, you are not well versed with TensorFlow or PyTorch, you can also start with Keras. Okay, Keras is more easier. This is also on top of TensorFlow and PyTorch. They are building it. So that's also fine. So one thing I'll suggest is that if you are if once you are experienced, you can use TensorFlow or PyTorch. If not, you can start with Keras for this one. Plus, you can use GDAL library. Also, GDAL, the good thing is that, with GDAL, you can also use, for example, for preparing data, you can use QGIS type of platforms, because you don't have to every time write program. For example, if you want to do PCA or something, you can directly use it using any of these other tools available. And when it comes to the model or other things, you can use Python. And Python you can easily integrate with QGIS also. QGIS is also having a platform where you can run Python scripts. Collins, is
Okay,
that
sir.
what you asked for? Or
Yeah, this is what I expected, and thank
yeah,
you, sir.
fine.
Thank you very
Thank
much.
you.
So we are done with the question and answer session, sir.
Yeah, thank you all for
Now
shooting
it's
the questions. And also, I understand that this is a very short duration, and an afternoon session too. Please feel free to email me in case you are interested in knowing more about it. Thank you once again. Yeah, all
yeah.
participants for the kind attention.
Yeah. So now it's time to express our sincere thanks to our eminent speaker, Dr. Arun sir, for his insightful presentations and demonstration sessions on deep learning and neural networks in geospatial data. Sir, on behalf of RIT Department of Computer Science and Engineering, I request you to accept this virtual memento as a token of appreciation and gratitude. Sir, we are truly grateful for your time and expertise that you shared with us. Your sessions has given a lot to think about: resolution trade-off in remote sensing data, benchmark data sets, spatial resolution enhancement, spectral unmixing and subpixel mapping resolution enhancement, multi-modal data fusions, and various applications on deep learning and neural networks in geospatial data. Thank you so much, sir. For it's a very, very informative sessions.
Thank you, ma'am, for the kind words and the kind invitation. I appreciate all for the kind attendance. Thank you. Thank you.
Yeah, thank you
Thank
so much, sir, for
thank you
joining
so
us the
much.
Thank
sessions.
you.
Yeah. So here I'm one announcement that please all are requested to fill the attendance as well as the feedback link that is shared in the chat box. So please share the feedback link. So now, dear participants, we will take a short break for 5 minutes, then we will resume. Again, welcome back. Good afternoon, everyone. Shakti sir, are you there?
Yes, yes, I am here.
Yeah, sure. So the session number 12 is start. I feel privileged to extend my warm welcome to such an inspiring personality for today's speaker, Dr. Shakti Sharma sir. Sir is an associate professor at the School of Computer Science and Engineering and Technology, Bennett University, where he leads the gaming and AR/VR specializations. With the Masters and PhD from CSRE, IIT Bombay in evolutionary agriculturals and their applications to satellite image analysis. Sir becomes academic rigor with innovative research, actively engaged in remote sensing evolutionary algorithms, data series analysis, game design, and gamifications. He has published over 20 research articles and served as a manuscript reviewers for IEEE, Elsewhere, Spingers, and other high-impact journals, and so on. Sir has experienced more than 12 years of his research and teaching experience. So now I'm requesting you to, sir, start the session.
Okay, hi. Thank you, Dr. Ekta, and thank you everyone else for attending the session and for this warm welcome. I hope I should be able to share my screen. Let me just go with that.
Session is on AI algorithm for spatial data classification and predictions.
So I hope my screen is visible to everyone.
Yes, yes.
Yeah.
Yes,
Okay,
sir,
so
yes, sir.
today's topic is AI algorithms for spatial data classification and prediction. I would be mostly focusing on the classification part and what are the challenges with spatial data. And we'll discuss a little bit about prediction, but there are more interesting topic that we will try to cover during this particular presentation. So, as the brief bio has already been provided, I will just talk about some of the research area where I have been working and the area which I am exploring or will be exploring in near future. So today also one type of artificial intelligence algorithm named as evolutionary algorithm we will discuss. These algorithms are bio-inspired from the evolution process, and we will particularly talk about one particular algorithm called ant colony optimization, which is inspired by ants. I have been working in the domain of satellite image analysis, whether it is for classification, super resolution, domain adaptation. Nowadays, domain adaptation is much in demand. Then further, I am also working in the domain of game design and gamification, AR, VR. If time permits, we will also discuss some of the applications and design pattern for AR, VR AR, VR tools for remote sensing images. So that's all. I have prepared. I know you have you are attending several sessions from Monday, and it would be very hectic, and you might be aware of many things. But still, I have started from very basic so that I can pinpoint the challenges that I want to address. Okay, so we know that the satellite images comes in different resolutions, and one type of resolution is called the spatial resolution. That means what is the total area that every pixel is capturing on the ground. So a 25-meter resolution would look better than 100-meter. because here 100 meter cross 100 is represented as a single pixel. Here the same will be represented by the same 100 meter would be more than 9 pixels, and here it would be more than 16 pixel for the same area. So we know that every pixel holds one particular digital number in every band, and that is how we see images. So as you can see in the right hand side image, we can't see much, but in the leftmost image, all the features we can easily identify. The another type of resolution is known as the spectral resolution, where we have multiple number of bands in different wavelengths, right? And if I say there are multiple types of images based on spectral resolution, there are images those are captured only in the visual spectra. There are images which has more than 200 bands available, so a smaller bandwidth and more data points for each object. Okay, so if we talk about every object on the ground, when we capture the reflectance from that area, it provides different reflectance in different wavelength. If we combine them and plot them, we get a curve that we called as a signature of that particular object. So or maybe pixel here. So the ground has a different signature that you can see in one image. The crop has a different signature. So we identify or classify objects independently based on these signatures. Okay, so if the signature would be similar, it would be difficult to identify or classify those two objects differently. So this is one way. And similarly, we can say in a multispectral images, we will not have the entire curve, but we will have only 3 to 5 points. And in the hyperspectral, we will have 200 points on the same curve. So the similar type of materials can be easily distinguishable if we have a hyperspectral image. That means we have more number of bands, usually more than 200 bands, right? So spatial resolution is where large areas are being captured. Spectral, where more number of bands or more information in the spectral band we have for the same particular pixel that you can see here, right? So same pixel but multiple reflectance in different wavelength, right? That is mapped to the spectral signature. Okay, so these are the two things. One is the spatial resolution, one is the spectral resolution. Now the challenge is that we can't get both better. Though we have such images where we can have a high spatial and high spectral resolution, but there are always challenges that that limits us to get or compromise in one of the parameter. So the challenges are like either there is not sufficient signal to noise ratio. So that means if the area is very small and we want the reflectance in smaller bandwidth, the problem would be that we will not be able to capture it. The smaller wavelength we will not be able to capture because the noise from the area would also be significant. So we will not be able to get the significant signal to noise ratio, right? So that is one reason that we need a bigger area on the ground if the wavelength are being smaller. Further, if we get that type of sensor that even reduces the noise and rectify, and we get better signal to noise ratio, the problem would be the cost. The cost of such a system would be very high. Another thing is like we are increasing the number of bands, we are also increasing the number of pixels in the image. So the size of image is directly you can say number of pixels multiplied by number of bands multiplied by every cell, whatever number of bytes it is acquiring. So if every cell is 1 byte, then you can multiply by 1, right? So size is also dependent on number of pixels and number of bands. So as we increase both, then size will also increase exponentially, right? So it is the multiplication of the number of pixels and number of bands. So what we usually get is we have to compromise in one of the parameter. Either we don't get that good spatial resolution or we don't get that much good of spectral resolution. Now, one more thing is that other than the spectral signature, as we discussed in this image, that every material will give a different type of signature in the spectral reflectance, right? So the different type of water will also have a different spectra, but still there are some spatial features that imposes the challenge that we can't just classify based on the spectral feature alone, because there would be impact of the vicinity, right? So if there is some pixel which is giving very high reflectance in say infrared band, but it's located in very urban area, then you might have to cross check that, if the area, surrounding area, doesn't justify for a vegetation, right? So we need to look at what other things it can be. So vicinities are very important, right? So close to a river or close to a water body, there are more chances of a marshy land or the vegetation. Similarly, the textures. So various similar looking objects where their spectral signatures might also be same, but there will be difference in the texture. So we can again classify them in different classes if we consider the spatial feature. Further, there are some impact of high level spatial feature in the classification. Like if I want to identify, objects, particularly if I say chair or table made by the same material, you can distinguish if you consider the edges or boundaries of that particular object, right? Similarly, like if I say there are various aircrafts in an image, you can identify the type of aircraft or the size of the aircraft if you consider the spatial features also, other than the spectral features, right? So these are some very important features that we need to consider. So by these by this discussion, I wanted to highlight that the both spatial and spectral features are important, and there is a trade-off that we need to address. So what we do is usually we take a combination of both spatial and spectral parameters, and we fuse them, and then we use different methods to classify. Okay, so if I say how we are fusing the spatial and spectral features together, so there are three dominant methods. One is the segmentation. So in the segmentation we can classify the object, so we can initially segment these pixels, right? So instead of doing a pixel based pixel classification, we can take a group of pixel as one particular segment, and then we can classify that entire segment into a class, right? So we will not be using the spectral signature of a pixel, but the spectral signatures of the segment. So that is one. Another is like, first we classify the individual pixels, or once the pixels are classified, then we relax it by using the classification by using different techniques in the classification map. Okay, we will talk about it in details as well. Then there are different way where we can uh, involve both spatial and spectral feature while training the AI model itself, right? So there are different methods like feature stacking. There are different joint spatio-spectral feature selection where your algorithm will select the features. We will talk about the kernel-based classification where we can increase the kernel degree so that we can add more parameters for the spatial consideration. We will talk about the representation-based classifier, some of the 3D feature extractions that we usually do in ANN, and definitely deep learning based classifier, which requires some convolutional filters like CNN, where we will be using the spatial features. Then further, there is a decision fusion. So we will talk about all the three eventually in this presentation. Okay. Then we will take a case study of end colony optimization, and then rest based on the time. Okay, so anybody has any issue so far? Okay. So if you have any question, you may raise the hand or just ping on the text, because I'm just seeing the presentation as of now. Okay. So the first method, as we talked about, is a segment based method. So where what we do is we classify different objects. So first we use an algorithm based on the similarity of the pixels. So we plot these pixels in the feature space, and based on that different characteristics or the behavior of these feature vectors in the feature space, we classify or group these similar features in one particular segment. So we don't know whether means multiple segments can belongs to the same class, right? So all features, those are having similar spectra, or here spectra is like in the feature space. So feature vectors, so similar feature vector, based on the distance, based on the other likelihood parameters, we will segment them together, and then we will use a classifier to classify those segments. And then one segment might be classified into so every segment will classify into one class, but one class might have multiple segments. So that is how it works, right? Then there is a something where we um, first do a classifier in the relaxation of classification map. Once the classification result is there, then for every pixel we will look at the neighboring pixels, and we will reclassify or relax the map based on the neighborhood, right? So each pixel is being classified based on the subpixel group, right? So we create a structure of merging these subpixels in a superpixel, and then one superpixel will be classified into one class. So both methods are similar. The only difference in the object classification is that the segmentation or the grouping of pixel is done before the classification. In the second one, it is done after the classification, right? So that is how we differentiate between these two. Then we have the feature fusion. In feature fusion, we use different techniques to extract the features, right? So like one of the technique is like we can use the principal component analysis and can extract different features. Those are based on the spatial orientation of the image, right? If you have seen the principal component analysis, how to transform the image from normal image to the spatial structural image, where you can go in the frequency domain basically, and then you can look at the different features. We can stack them, can use any classifier here, and then classify. So again, it will have the impact of the spatial orientation of the pixels, right? This method is still widely being used because it is simple to operate. It doesn't require multiple features at the later stage. Principal component analysis gives you already limited number of features, and if, as you know, that the initial features, those are being provided by principal component analysis, are more dominating features, and the rest of the features as we go down would have more noise than the information. So you already get limited number of features, so training can be done with limited sampling. So this is very good for all those cases where the sample size is limited, the training samples, and we can use it, right? So we can also use the hue saturation intensity based image rather than the normal RGB image. That can be converted easily, and then we can use the PCA. Okay. Further, the other method is a kernel based classifier. In the kernel based classifier, we have seen that we map these pixels based on the their feature vector in the feature space. Then we add the spatial feature component, and so we add one more dimension to it. And so the same as you are seeing, there's these two. If you look at only in the two dimension, these two are looking similar, right? There is no segregation between these two. Like if you classify, probably it will get classified into one class, right? Because there is no significant boundary that you can see in these two elements, right? But as we add some spatial features as one of the another matrices, maybe based on the texture. So suppose this class has a different texture than this class. So once we add another dimension of the texture, you can see that these two now are appearing differently when we have increased the dimension. So we use a higher dimension kernel to include the spatial features, right, as a texture feature or other features. Okay. Then so what we use is a stacked features. It can have, there can be a direct summation of the two features, right? The spatial and spectral. There can be a weighted summation, there can be a cross information. So all four methods are possible based on how you want to incorporate that information. Okay, then the third one comes as a representation based classifier, where we usually use a linear combination of training samples. Okay, and we assign the large weights to the neighborhood pixel, so the chances that a pixel is being classified to neighborhood is more based on its neighboring pixel, right? So, and you see that happens in reality as well, right? So if a pixel is very close to, say a road and a water, so one side there is a road, one side there is a water, and in between there is a pixel, so it would be a high probability that that pixel either belongs to the road or it belongs to the water body, right? So this is how uh, the neighborhood structure works. So what we are doing here is that we are providing more weightage, weights to the neighboring pixel classes, right? And then the central pixel has the more possibility of being classified in the neighboring classes. But again, if its spectral signature is significantly different, then it will not get classified into the neighboring pixel. So again, we are increasing the probability, but it's not being fixed. So again, we are working with the trade-off here. Okay. Then there are methods where we can extract the 3D spatial features by using different kernels. We can use different type of modifications, like we can go with hue, saturation, intensity images, and then we can use the a particular direction, maybe in the height direction, a width direction, a spectral direction. So multiple features we are extracting in different direction, then we are combining them based on the high and low. So different parameters of features we are creating. Okay, so these new features are the extracted features, would further be being used in a classifier. Okay, so if you see, most of these methods are, what we are doing is we are creating new features and adding it into the classifier of the existing classifier, right? Deep learning based methods are mainly majorly being used where we have sufficient number of training samples, right? So what we are doing here is very similar to the spatial feature extraction, but here we are not defining what type of feature we need to extract, rather than we are defining the overall kernel for the convolutional filters, where multiple kernels will be there, 2D or 3D, based on the spectral and spatial correlations, and it will be utilized on the image. We will be using the pooling and then again convolution, and there can be more combination of scaling, pooling and convolution filter. So multiple based features we extract, whether it is a line based feature or it is more of a polygon based or 3D dimension based features. So based on that, we can increase the number of convolutional layer, and based on what type of feature or textures are available, you can use different kernels in each of the convolutional layer, and then we can classify. The advantage here is that we don't need to dig down on the exact structuring of the particular class, because if you have sufficient training samples available, the system might adjust the weights and can identify or give more weights to the correct convolutional filters, right? However, if you already know that what type of features are highlighted, and the limited training samples are there, then you can extract the relevant spatial features, and can along with the spectral features, you can provide that feed into a network that would be a faster uh, training based on the your expertise, right? So that is what we can use instead of a deep learning based method. Okay. Then the last one is a decision fusion method, where we have multiple classifiers, and each classifier is using some method to classify the image, and some might be based on the completely based on the spectral, some might be completely based on the spatial, some can be a combination of these two, as we have seen, like some of the methods. So it can be coming with multiple classifiers. The training samples is also coming from different pool. As you can see that different classifier are using different band combinations, okay, and different features. So eventually there would be a decision fusion, which can be based on the voting method, which can be based on the dominant method, which can be based on any other method. So similar to ensembled classifier, here we are using a decision fusion, which takes the ultimate call on based on the classification result by multiple classifiers. Okay, now I guess I was able to explain what is the spatial spectral trade-off, and what different type of classification methods we use to incorporate these things. Okay, so here I will be presenting one of my work. So I had developed an algorithm called spatial spectral end colony optimization algorithm, which is an extended version of end colony optimization algorithm for classifying the images based on both spatial and spectral parameters. Okay, so let me explain what is end colony optimization. There, then only I will be able to explain you that how it is being used for different cases. Okay, so moving on. So if you look at the most of the evolutionary algorithm, they work very similarly. Their selection criteria or their generational criteria can be different, but their approach is usually similar. So if you understand one algorithm, it is easy to understand the other one. That is what I can say. So given this example, this algorithm is inspired by the real ants. And if you have ever noticed, the ants always move in the straight line format, right? So if you have sometimes wondered why ants are moving in a straight line, so, okay, so can they actually identify some way of moving in a straight line? So actually, whenever we go in a bio-inspired algorithm, the idea is that they are intelligent. All biospecies are intelligent, and that's the reason that they were able to survive. If you look at their structure, how they get the food, or how they live in an ecosystem. um, different roles in the life of a species will teach you different tactics. So ant has a tactics of finding the shortest path from the nest to food, and that's the reason, if you have noticed, that ants always follow a straight line path. Okay, so they don't go in a rotational or these very different way. Usually you will see a straight line from one point to another, and considering that ants are very small, and finding such a straight path is not directly driven. So there is some intelligence that is happening. So we try to mimic the same intelligence, use the same to train our images, right? So let me go back to my presentation. Yeah. So So initially, you consider that there are several ends. Obviously, all these evolutionary algorithms are based on the population. So there are multiple ends here, and you consider that there are two paths, A and B, to reach the food. And initially, ants don't know what path to follow. They can randomly follow any path. Okay. While traveling back, also you can consider that they don't know which path to follow, and they follow both paths randomly. Now what will happen, that one path length is more, so suppose here it is 50, here it is 30. What will happen eventually is that the frequency on the shorter path will be high, because this ant will move faster, right? So again it will repeat from nest to food, so its frequency would be more, right? And the frequency on the longer path would be small. Now what these ants do, like when we go back from food to nest, they uh, use a particular chemical compound called pheromone. So they deposit this pheromone on the path, and this pheromone attracts the nearby ants to follow the same path, right? And it is volatile in nature, so that means like over the period it also gets evaporated, right? So initially ants follow both paths randomly, but eventually the deposition of pheromone on the shorter path would become more based on the frequency. तो जो shorter path है, it will get more and more pheromone deposited, and more ants will start following that path, and eventually, due to the volatile nature of the pheromone, it will get evaporated entirely from the another path. Okay, so on the longer run, eventually there will be only one path remaining, which will be the shortest path, and that is how ants always follow the straight line and follows the shorter path. Okay, so this is the overall algorithm used by ants. Again, like for our challenges we can't work directly, so we need to convert it into a mathematical structure and use it like in the mathematical form. So if I say that there are two particular parameters that we are using, is the theta and eta, and theta is based on the pheromone on a path, and eta is eventually later has been introduced, which is based on the heuristic function, um, or you can say the local likelihood. Okay, so what we are saying here is, let me explain it by using uh, transition state diagram. So the first time this algorithm was used for solving the traveling salesman problem. I hope you all have heard about the traveling salesman problem. Are you aware with the traveling salesman problem?
Yes, sir.
Yeah. So it is an NP hard problem, where what we know is that, considering there is a salesman and he wants to visit n number of cities, it can be 20 maybe, and if he wants to follow a path which cost him the least cost while visiting every city once, you need to find the path for the salesman. Now, there are n cities can be organized in n factorial different way, and if we use a brute force algorithm, the n factorial would be the complexity, which usually goes upper bound of n raised to power n. So it is very complex problem. So instead of finding the convergence, we look for the optimal solutions, right? In the given time frame, like we run algorithm for a limited time period, or we have a criteria like until we achieve a path with a distance less than a few kilometers or few hours, we accept the solution, right? So that is how it works. So considering that, we have defined weights of each path. Okay, so S1 to S2 is something like, so source 1 to source 2, the ant wants to go, or there are two source you can say, and there is a target, and there are intermediate states I1 I2. So what is happening here is, like, suppose my ants are on the S1 and wants to move to I1 or I2, so it needs to find a path, right? So what is happening here is that there would be one likelihood, local likelihood. So it can be like, suppose this length of this path is say 20-meter, and this distance is say 50-meter. So likelihood of a closer path would be high, right? So this is 20-meter, this is 80-meter. So again, it has a high chance that it will move to a city which is closer, right? So this is one way, which we call as a local search or a heuristic function. There can be any heuristic function. So what heuristic function we are using here is 1 by distance, right? Which is very nominal heuristic function. Okay. But you can consider, it might happen that S2 to I1 is 20, but I1 to T is say 100. And here S1 to I2 is say 80 or say 60, but I2 to T is only 10. So the shortest path would be S1 I2 to T. So again, whatever we are saying here are the probabilistic. We can't be sure by selecting the closest city only. Okay. So that we need to keep in mind. So heuristic function or local search function, gives you approximation that this might lead to a good solution, but doesn't necessarily to be the correct answer. So what we call it as a whatever best solution appears from the current state. So suppose heuristic function we are taking as 1 by distance of the transition. So here it is say 60, here it is 20, so the 20 is more likelihood. So that is what we are saying, that a particular ant on node X will select a path Y in the kth iteration based on the pheromone deposited, like how many previous ants have selected the same path. Further, there is a local search function and there is a some reward mechanism. Okay, so when we say the pheromone, what is the value of the pheromone? If you see, so pheromone we are saying is q by lk here, and lk is what is the total path of that particular ants. So consider that one ant is taking path from s1 to i1 to t, another ant is taking a path from s1 to i2 to t, and this solution was better, suppose in this case. So the more pheromone will be deposited on this particular path, less pheromone will be deposited in S1, I1 and T. So whichever path is shorter will generate more pheromone. Whichever is longer path will generate lesser pheromone, right? So this is what we are saying, that the pheromone deposition is inversely proportional to the length of the tour of that particular ant, right? So whatever tour it is taking, the minimum tour ant will deposit more pheromone. So whatever be the best solution of the, so initially we start with 100 ants, say suppose. So whichever ant will produce the best result will get the most pheromone, and based on that criteria, every ant in the next iteration will try to follow a similar path, will have more probability of following the similar path, right? So we are finding solution close to the previously best solution, right? Again, you will say that there are chances that we might get trapped in the local maxima, local minima. It's a possibility, but that is the reason that these are the probabilistic solution. So even we increase the probability, we don't increase it to 1. So even if we are getting very high pheromone on a particular edge, there are still chances of another edge being selected, and if it generates the shorter path, it will get the more pheromone, right? So this is how this ant system works. Okay, so I hope it's usually clear. And this is the evaporation part, where we consider some portion that will get evaporated in every iteration from all path. So if a path has been selected one time, but in the next iteration or the other iteration, most of the component of that path are not being selected, then those components will evaporate. So will so the impact of the 10th iteration solution will not be applicable in the next generation like that. So the impact of seniors are reducing slowly. So let's talk about the spatial spectral and colony optimization algorithm, a modified version that I have told you I have created. So here what we have done is, like, for every pixel we consider a sorter map like this, where every pixel is connected with all different classes. Okay, so ant will start from this node and move to one of the class node. Okay, that is the only consideration. Now the selection of the ant from one this node to the class node will be based on two parameter. One parameter is the spectral signature by SVM or SAM method. SVM is the support vector machine, and SAM is a spectral angle mapper. I hope you are aware of both the methods. Both are based on the spectral signature of the pixel. Okay, so it is not based on the spatial. So the first parameter is based on the spectral feature, either support vector machine or the spectral angle mapper. And then we create a matrice of the pheromone on each edge. So for every pixel, this map is being followed. So every pixel is connected to number of classes k. So here for every pixel there are k edges. So this is the map for all the edges, and every edge has a initially pheromone deposition, right? So this tau 2, 1 is representing the pheromone between pixel 2 and class 1, right? Then what we are doing is we are defining another function which is based on the frequency of the neighboring classes. Okay, so if suppose this is the pixel that we want to classify, and in the neighborhood there are 3 pixels of class 1, 2 pixels of class 2, 3 pixels of class 3. So giving that this pixel, we want to give a weightage that it has a high tendency of being classified in one of these classes, right? So based on the frequency, so what we are saying that tau ij is directly proportional to the frequency of the class. Okay, and but inversely proportional to the distance of the pixel, right? So these are the adjacent pixels at the cost 1, and these are root 2 distance pixels, right? So we are also taking the weightage, because in the spatial real images the spatial closeness is actually based on the actual closeness of the pixels. Okay, so that is how we are considering. So there can be 4 cross 4 neighbor, there can be 8 neighbors that we want to consider. Okay, and then we use this formula to calculate the pheromone uh, uh, the closivity of the pheromone. And then we are using a spectral angle mapper, which is nothing but the angle between the um, edge pixels or the training samples to the actual pixel for which we are calculating the or classifying. So what we are doing here is that we are calculating a vector median of the training samples for each class separately, and then every pixel is being angle is being mapped to these classes. Okay, and then based on what the angle is being formed, we define the eta in the same way. So for pixel I, if the angle to j is 30 degree, and for some another it is 60 degree, then 30 degree has a more choice or more probability of being classified in that particular class. Similarly, SVM, I hope you are aware of the SVM. In the same matrice, we use multiple SVM because it's a multi-class classifier. So we have to use k into k minus 1 by 2 if I have, so every pair of classes we have one SVM, right? So suppose I have 16 classes in one of the examples, so that means 16 into 15 by 2, 120 SVM machines are being considered. Okay, and the probability are being calculated from the SVM. Now remember, in this method the classifications are not being completed by SVM, are not being completed by SEM. So these are providing a probabilistic choice for a pixel, which is further being mapped into eta. And if you remember, the selection is a multiplication of eta and tau. And tau we have already defined based on the closeness of a pixel. So we have defined tau, we have defined eta, which has given a probabilistic model, and based on that a random number will be selected with this density, and the pixel will get classified. Okay, now look at the results here. So if I show you so these subheadings are not being visible clearly, but this C image, if you see, this is the actual ground truth. Okay, and the image B is the output of the SVM classifier. So you can see that there are multiple pixels here in this particular class or in this particular class. Those are, or here also in these classes, which are being incorrectly classified, right? But if you look at the here after using SSACO, all the incorrectly classified of this image are completely eliminated. However, here you are seeing that some of the classes are visible, some incorrect classes are visible here and here, and due to and these are for very specific reason, because this is a limited images, and there are no samples in the background here. Excuse me.
Real short session can go to that to understand exactly what kind of things we talk about, how can we arrange
I guess someone's mic is on.
Sir, your voice is not audible. None of
also
sir.
submitted
My voice is not audible.
You are audible. No issue. No issue.
I think
I
somebody
guess,
else is also speaking.
yeah, yeah.
Yeah,
The
yeah.
speaker is
I
on.
guess some Jagannathan, I can see his mic. If you can, yeah, okay, thank you. Okay, so what we can see here is that there are very limited, samples available here for the neighborhood, and most of the neighborhood is also incorrectly classified, and that is the reason that the misclassification are still there at the neighborhood. This is one of the very challenging data set called the Indian Pines, and you can see the SVM provides you this type of paper and salt based classifier result because it is only based on the spectral features, and most of the classes here are of the same crop at different age or very similar spectral signature. And once the SSACU are there, you can see that various uh, um, incorrect classification from this class you can see entirely here. Let me highlight. So this portion, if you see here, many pixels are incorrectly classified, right? Here also, here also. So all are being correctly classified. All these paper salt effect are being eliminated, and to better appear this particular stage, if you see here, this particular class is also getting quite good response. However, still you see that there are some misclassification in this. Eventually the SSACU has eliminated all new pixels which were actually correctly classified, and this happens sometimes because very limited samples are available of that particular class to give a weightage to that class. Similar things are available at this location as well. So these are a few examples. Okay, and now I'm moving to one more small presentation. As I was saying, like if time permits, I will come back on one another interesting topic based on so as the topic was of AI and classification, but since I'm currently exploring this domain of XR, I thought like it would be a good platform to discuss about some of the stuff which might excite some of the faculty members also in the domain of using XR. Again, these applications are based on the AI based classification models for most of the cases, and it would be based on the development of Unity and Unreal Engine. Okay, so I will quickly explain it to you, and we'll close in maybe next 20-25 minutes. So there are three particular terms I would like to define are the virtual reality, where you get a headset which completely blinds your vision, and you completely see a virtual world which is there in the device. The augmented reality, probably if some of you have played Pokemon Go games or are using Zomato AR, where you can see the dish in your on your table, or if you are using any of the application of Furlenco or Amazon to look at the furniture in your room before buying it, or you are checking the lens card for the checking the glasses on your face. Similarly, the mixed reality is again the combination of both virtual and augmented reality. There are very less number of devices available for mixed reality, like HoloLens 2. And for augmented reality, our normal mobile cameras are fine. And for virtual reality, if I say Oculus devices are there, multiple Vive headsets and other companies headsets are available. Okay, so this is one example where one of my student is using the VR MR headset. Okay, I need to remove the highlighter. Yeah. Okay. So here you, so again, these things require the spatial computation. As you can see that you are virtually writing or virtually interacting with the system. So in this case, the student is working on a computer which is not visible to us, but he is interacting by using the headset. This is the VR headset that you are seeing. If I go further, these are some of the applications in the remote sensing cases where different line segmentations or line feature detection, detection of different bodies, different objects, classifications into different areas are being done. And by just viewing a headset, you might get all these annotations, you might get the information. Suppose you are going and finding a fault in a particular line, you might be able to correctly map based on the spatial information involved. You might pinpoint the exact or you might visualize the exact pipeline location, which eventually is very helpful in various scenarios. So all these applications are being created. So this is one particular application taking from XR for drama. You can find the paper at the end of the this paper. There are multiple VR tools, those are being used for teaching the remote sensing area. So there is one project Kepler formed to create the Mount Fuji, where people can see the Mount Fuji, different type of geographical structures, different type of areas in that location. There is another project Kepler, where different type of scenarios are being created for learning, teaching the environment to STEAM education students, that is under 10 students. There are solar system like this one I have created, also in AR. We'll show you at the end of the presentation. Being used to create different type of training. So if you can see here, one of my student has created a project where the training for different scenarios like earthquake, fire, or flood is being given. So once you wear the headset, you get the feeling of sitting in this room. I hope the voice of the system is on.
Yeah,
Yes.
we can hear. We can hear.
Yeah. So it has different tasks that you can schedule. You can utilize these things to map to the real geographical scenarios, real building diagrams, the historical sites. So different type of trainings can be programmed. There are some other applications further in this technology, like if I talk about digital twin, where we are creating the physically similar as well as sensor based system. So as we were talking about various predictions. So one thing is to predict using an AI model, and the other part is that visualizing the predictions or the uh, different kind of scenarios in realistic way. So there is one visualization and risk assessment of landslide data for Nepal that has been created over the VR technology. Further, there is a particular toolkit by NASA Goddard Earth Observation System.
Any guesses? Some wild guesses.
Which has been created. So you might follow these based on your interest. The digital twin is a technology where these sensor data is being directly used. So when you are seeing a particular scenario like I have shown you in these type of images, and whatever sensors data feed you are getting, whether it is about temperature or if it is a flood zone, as you can see in this particular image, you get the live feed of the area, that how much area is dipped. It classifies these maps, and then based on that, whatever course of action you want to plan, you can plan directly at the spot by because we are getting a detailed version of the remote sensing information extraction is happening here. So all that information you might utilize, and if you are anything changing from here in your device in a digital twin, the same impact will also be visible on the real world. So it works both way. You can either operate the real scenario from your system, or the reverse, like from your system you can work on the real scenario. Okay, so this is what you can do. I'm just put this particular scene here. So this project, if I say, is the 1 hour project which usually students do while learning Unity, and how well it can be used to train people about different geographical features. Okay, so this tool usually takes 1 hour to create this type of a project. Okay? So for student as well as for teachers to create different applications in this uh, tool or this use these technologies. Further, you might follow one of these references as I was using a particular application. Let me see here. Yeah, so this is like XR systems and cultural heritage. So that is one very good domain where people are creating the real scenarios, and then using different predictions model, identifying not even the future prediction, they are also mapping it to what was the past possibilities, that how it would have appeared if the structure were completed, especially for the cultural heritages those have been destroyed over that time period. So you might fulfill and complete the structure virtually, and can see what would it have been appeared before that. Further, there is this particular application which I was telling you is a geological characterization of Nepal landslide. So then they are using virtual reality and mixed reality approaches to visualize and run different type of assessments on that, where you can simulate different scenarios. You can also map onto what would have happened if rainfall would be more or less. So all those scenarios can be mapped here. Okay, so and this particular application of Kepler can be seen to learn the geographical features. So again, I say this is relatively new domain, but it has huge amount of scope. And I have used a particular term, if you have seen, is the XR here. And whatever I have talked about is a virtual reality, AR and MR. So if I replace all VAM with one X, that takes us to the XR, which can have multiple technologies combinedly available for one particular application. Some more applications are there in creating the digital twin of the airport systems, where every landing flight, every moving person, all the different movements you can visualize, predict the scenarios at different considerations. You get different sensor data live, and then based on that you work on those application. Okay, so all these applications you may explore. I guess here I stop my presentation and open for the questions. Yes.
So thank you so much, sir,
Yeah.
for such a wonderful and knowledgeable sessions. So participants, if you have any question, then please ask directly.
So do we have any questions? So only in two scenarios there are no question. Either people understand everything, or I was little fast and they didn't understand much.
So, thank you, Dr. Shakti Sharma. So, in the simulations that you have shown,
Yeah.
so and in previously also shown about ant colony optimization, do we make a optimization problem to generate that digital twin scenario?
Okay, that's very interesting question. Yes, we do. Actually, most of these uh, um, digital twin, where we work on different simulation cases as well, either to optimize the productivity or to optimize, like in a plant, or to optimize different other scenarios. We use these optimization techniques, whether it is ant colony optimization or other AI techniques, to run the simulations. It's very similar, like if you have seen or used any of these gadgets of simulation of a car racing in a gaming zone. So it's similar to that, where we are creating or getting the information from different sensors, and we are combining them by training a model on the similar data, and find the optimized pathway. You can consider that I have a plant with multiple chain pipeline, where different scenarios are happening, or different time is being consumed on everything, like in assembly line. And then you want to find an optimized structure, or if it is a plant, I want to find the optimized setting for the temperature and the vessel that my vessel can hold, because all the physics features are applicable in these digital twins. So whatever happening in the real world, all these can be mapped, again limited to the physics feature it understand, all that can be mapped, and an optimization algorithm can work well with these scenarios.
Okay, thank you.
Yeah, thank you so much. Any other question? I guess there are no more questions.
Yeah. Okay, thank you so much,
Yeah.
sir. Now it's time to express our sincere thanks to our eminent speaker, Dr. Shakti Sharma, sir, for his insightful presentation and demonstration session on AI algorithm for spatial data classification and predictions. On behalf of our AIT Department of Computer Science and Engineering, I request you to accept this virtual memento as a token of appreciation and gratitude, sir.
Thank you so much for the appreciation. Today we are also holding convocation program in our institution.
So here I would like to take this opportunity to thanks today's speaker, Dr. Shakti Sharma sir, for sharing his finding and opinion with all the participants. I would like to express sincere thanks for giving such excellent coverage about the three spectral, spatial feature extraction, deep learning-based classifiers, and decision tree methods and various applications and demonstrations based on AI algorithm for spatial data classification and predictions. So I hope learners, researchers, and faculty participants in the field of GeoAI or relevant fields which have great benefits from this session. So once again, thank you so much, sir, for your valuable
Thank you
insights.
so much.
And thank you all the participants. Feedback link is shared in the chat box. So again, a 5 minutes break, then continue the sessions. Thank you so much, sir. So now hand over the mic to
Okay,
Prakash.
okay. Thank you, ma'am. Yeah. We will have a 5 to 10 minutes break. After that, we can start the next session. You want to switch on the AC fan? Yeah, yeah. And now I'll be speaking now. After that, you can switch on after 5 minutes. Yeah. Hello, Dr. Deepak, you're there in the group?
Yep, yep. Can you hear me, Dr.
Yes,
Prakash?
yes, yes. Can you hear me?
Yeah,
Yes,
I'm audible?
you're audible. Yeah. So would you want to check
Yeah,
your
yeah.
presentation and screen?
Yes, yes, yeah, yeah. Just
Yeah,
a
sure.
minute. Yeah. Hello, Dr. Prakash, can you hear me?
Yeah, yeah. Yes, yes. Can you enable your screen sharing? We'll check if your presentation works. Yeah. You can share your presentation once.
Yeah. So, can I share my
Yeah,
slide
yeah.
from?
Your PPT slideshow.
Uh, I have actually updated few things.
Okay.
Can I do that?
Sure, sure. Yeah.
Yeah, just 1 minute.
Are there any issues you're facing?
Yeah, yeah. No, no, I'm almost done. I'm just,
Yeah.
I want to see, yeah. Is
Yeah.
it there?
Yes. Yeah, yeah. We can see you.
Can you
Yeah, we can see the screen. Yes. Can you change the slides?
yeah, just 1 minute before the presentation. Yeah, I'm done from my side.
You're changing the slides. Can you change your slides once?
Hello?
Yeah, yeah. Can you change your slides? We're only seeing the first slide.
Okay.
Can you go to the next slide?
Yeah,
Yeah, yeah. Okay,
yeah.
thanks.
Is it moving? Is it
Yeah,
moving?
yeah. Yes, yes, yes. You can unshare your screen. We'll have
Yeah.
a small introduction and then you can start.
Okay.
Yeah, thanks. So we'll
Okay.
start with today's yeah. We'll start with today's session, the last session. Once again, good evening and thank you for all the participants who've been attending these sessions for the last 6 days. And this last session is a little bit different from all the talks that we've been hearing from the beginning, because this talk mainly focuses on some of the policy aspects and the relevance of these geospatial techniques and technologies to our country and also for a wider scale, to the global scenario. So today with us is Dr. Deepak Samal. He's an assistant professor at the School of Public Policy and Governance, Tata Institute of Social Sciences, Hyderabad. He holds a PhD from the Center of Studies in Resources Engineering, Indian Institute of Technology, Bombay. Before joining TISS, he was working as an assistant professor and program coordinator at the Center of Environmental Planning and Technology, CEPT University, Ahmedabad. As a postdoctoral fellow at Ashoka Trust for Research in Ecology and Environment, he has worked on upscaling catchment processes for sustainable water management in peninsular India. He was involved in several consultancy research projects as a leading team member for the precision mapping of city infrastructures, water and sewer, mapping and monitoring of pollutants in Ulhas Waldhuni River, NGT issue, land subsidence studies, and creating a high resolution topographic model for Mumbai city using advanced geospatial technology. He has also worked with National Environmental Engineering and Research Institute, where he was instrumental in developing a thematic database for environmental research. Dr. Deepak is passionate about the application of geospatial technology for mapping, monitoring, and modeling natural and urban processes. His area of interest includes geospatial technology, water resources, spatial statistics, and urban planning. It's really indeed a privilege to have you with us, Dr. Deepak, and we look forward to hearing from you. Thank you for joining us. Yeah, yes. Deepak, you can uh, start your presentation.
Yeah. Thanks, Dr. Prakash. Can you give me 2 minutes just to share the presentation? Yeah. Yeah. I'm audible and clear. Uh,
Yes, yes,
couple
clear. Yeah,
So, Dr. Prakash, if it is fine, if I'll keep my video off just
yeah,
for,
yeah. You can keep your video off. Yeah.
yeah, yeah. Thank you so much for the introduction. And I know it's a Saturday and it is afternoon and lecture. So I'll try to keep things very crisp and I'll also try to give the policy relevance of the geospatial technology. And because here we are in Tata Institute of Social Sciences, Hyderabad, we are working a lot of aspects of policy that how geospatial technology can be deployed. And specifically here they're saying it's a big data, right? For some kind of policy intervention or some kind of its relevance in the, I would say, in public policy. Okay, so I broadly divided my presentation into these 5 components. We'll be briefly talking about geospatial technology. I think this is I think this component might have covered in the previous lectures and its relevance to the public policy. And you'll see what exactly policy and programs and different stages of public policy in general. And we'll also talk about what exactly policy maps. So this is the new terminology when we are actually going to use geospatial technology for public policy. And it'll also show you different case studies where how policy questions can be addressed using different techniques of geospatial technology, which includes both remote sensing, GIS, image processing, and many other techniques. I hope I'm clear and audible. Just to,
Yeah, yeah. Much
yeah,
clear. Yeah.
thank you very much. So now I think this is what is our broader umbrella of geospatial technology, which consists of broadly 4 major components. One is our GIS or the spatial analytics, where we'll be dealing with different GIS database creation and the analysis, and followed by you have positioning system like global navigation satellite system and positioning system. And third component is the Earth observations, where we are deploying different satellite images, aerial mapping, and drones. And the fourth component is the scanning. The advanced part is with LiDAR or radar-based scanning. So if you just integrate these four things, so you'll actually get it under the umbrella of geospatial technology. And coming to the policy, that I was also in some kind of dilemma after my doctoral degrees, that how the policymaker thinks, right? Because as a technocrat, we work in a very different way. We are always focused on the technique and the problem that you want to address. But the policymakers look at in a very different lenses, right? They want certain problem to be executed in certain way. Sometimes what happens, our technique may or may not suits them because they want that certain problem to be addressed in certain way. I'll just briefly discuss about certain text related to the policymakers, what exactly a policy is all about. The policy is nothing but a simple, it's a set of guidelines principally used to achieve a set of goals or the outcomes. And when you talk about the data scientist, and the data scientist, if doesn't know, right, about certain components of the policy or the overall understanding of the policy, then it will be difficult to design the solution to achieve the policy goals, right? And when you talk about the programs, program is nothing but some kind of, we say this is an implementation arms of a certain policy, and the program is tool which is used to implement the policy to achieve the policy goals. And the decision making, which is the backbone of the policy or public policy, is a part of this program or any kind of policy where the data scientist can have the greater impact. So nowadays we are talking about evidence-based policy making, where we are going to deploy this big data or the geospatial data in a very big way. So that means the policy which is driven by the data sets, it's not just by the any other aspect, right? And when you talk about different stages of the policy, actually broadly you have these four stages. So there is one idea, and that idea needs to be conceptualized. And the third phase, that needs to be implemented. And the fourth stage, it needs to be evaluated. For example, here I can give you an example. For example, Swachh Bharat mission, right? It's an idea, right, of some leadership. And now that particular idea needs to be conceptualized, so that how do you make our India clean, right? And that conceptualization where you prepare some bit, right, for its implementation, right? And the implementation requires a lot of effort, and you implement that particular idea, right? Once it is implemented, right? And the fourth stage is we evaluate, right? Whatever the things that you have implemented, how it has actually impacted the common man and how it has impacted the actual objective that you made actually at the beginning of this particular this Swachh Bharat mission. Similarly, you have a lot of other things that you usually perform based on this four, I would say, broader steps, right? Yeah. Yeah. Now also there is related to what is public policy. Policy is one thing, public policy. Public policy is anything a government chooses to do or not to do, right? And when you're talking about public policy, our major orientation is towards public, right? The company has its own policy, but when you're talking about public policy, it is mostly, it is going to influence all the aspects of people's life. For example, you lowering the tax rates, or you talk about something related to the regulations, regulate the environmental pollution, or you talk about subsidies to the business, or you restrict immigrants entry to the country, or allocating budgets for the different sectors. These are what broader aspect of public. I'll just briefly discuss about the decision making. How do I actually take decision, and there are different types of decision making, and what is the current trend, right? So if you look at if you look at this, the point I have highlighted, that how do you take the decision? It's reactively or proactively, right? So in proactive decision making, you have all the evidences, right, of your past, right, and you can anticipate certain things, right? In the reactive, you take a decision once the event has already been happened, right? If you look at this other 4 points, like ad hoc based decision making, we have political decision making, We have institutional knowledge-based decision making, and the fourth one is our evidence-based decision making. So mostly in the evidence-based decision making, this is completely dependent on data. What actually your data suggests, right? Accordingly, we implement those policies or those ideas because it requires a lot of finances, a lot of resources, right? Yeah. Now coming to the policy maps, right? So earlier we had, I think, whatever the things that you produce from this geospatial technology, called it thematic maps mostly, because it contains certain theme. It may be related to water, soil, any of the socio-economic activities. So when you talk about policy maps, it's nothing but the policy map clearly shows where there are opportunity to intervene, right? So it will clearly say that especially that where and how such policy intervention needs to be implemented, right? So this is what is about the policy map. So I'll show you using a lot of case studies, 3, 4 I have case studies where I will be discussing and what was the policy questions, what was the policy maker wanted to solve, and how we have used the geospatial technology to answer their queries. So here just one case studies where the policymaker and the organization is Odisha State Water Supply and Sewerage Board. So they wanted to uh, give safe drinking water supply for a city like in Puri, which is a religious city, right? And how they are going to do it, right? So when that such type of question came to us, then you realize how to proceed about this, how to begin with this, right? Because this is a big question, right? Then what we did is we simply demarcate what are the water sources. If you look at this particular diagram, you can see we have this red cross that refers to the production well. We have hand pumps, we have open wells, we have open water body. That means whatever the water bodies in that particular region or in a city, that needs to be mapped, right? How we need to map it? So you map it using the help of GPS, that's the global positioning system, which records both X, Y, and Z. And what actually we did is from each and every sources, the drinking water sources and open water bodies, we collected the water sample and we tested it, right? Based on certain guidelines that and certain water quality parameters, right? For example, if you look at here, so there are two water field here. You have Chakratirtha water field, you have Balia Panda water field. So these two water fields actually responsible for providing water supply to the entire city, right? So, and the, what else the policymaker was asking us the question is, ki, sir, up to what extent we can actually draw water from this to water field? Why the question was like this? Because if you look at this part of it, it is actually Bay of Bengal, right? And you can't extract water because these are the production well, means you can refer to the bore wells, right? They're just pumping water, right? And this population is also growing as a city, right? And the water demand is also rising. So up to facilitate those rising water demand, so the question was, sir, up to what extent actually we can draw the water? Because if you draw more water, there will be saltwater intrusion, right, from the ocean towards the landslide, right? So that a tricky question that requires a lot of understanding of the entire process plus the use of geospatial technology, because through that you can visualize the overall scenario. So today, in today's presentation, I'll be only looking into water quality parameters, and I'll show you how in simple way I've demonstrated which are the city part of the cities actually we have a safe drinking water supply and where we have getting polluted water supply. I would say water sources, not supply. Yeah. Just a small clarification from the audience. Hope I'm clear and audible and things are moving clearly. Yeah.
Yeah, you're
Yeah.
clear.
Yeah. Thank you, Prakash. Yeah. And this is what the parameters actually we just identify for a safe drinking water. Like we have a pH value, we have a TDS value, we have hardness, we have alkalinity, calcium, magnesium, sulfate, nitrate. So these are the parameters actually we tested, right, for each and every what sampling locations, right? And we also measure using X, Y, and Z using GPS, and we attach those particular values against each and every location, right? The best part of the geospatial technology is actually you can visualize what is happening, Or in other words, I can say you can actually visualize invisibles. For example, water quality. If you just look at the simple sample of water, you can't say whether it's a potable, it's a drinkable or not, right? Unless you test it, right? So our major effort was to actually sample all those drinking water sources and have some situational analysis that how the water quality behaves or propagates in that particular city. And this is the data we took for two seasons. One is our pre-monsoon, another is for post-monsoon. And we have collected data. If you look at each and every column, right, which refers to a specific source of the data. For example, here city pump wells, city hand pumps, right, and city open water body. That means all the points actually here you can see we took it from, sorry, we segregate them, right, like different sources, right, for the better understanding of the problem. So this is the data actually tabulated it, and this is for the, and this is what the all aggregated data set, right? And this is for the post monsoon. We did the same thing for the post monsoon. That means for pre monsoon we collected the data. We also collected the data from the post monsoon, right? Just to see even how the water quality parameter changes before monsoon and after monsoon. And after all we got all these points, actually the challenge was how to visualize those points. How do you show that this is what the scenario to the policymakers, right? City commissioner, right? And this is what map we have prepared. Some of you might be knowing, I think although maybe audience might be knowing, we had a simple technique we called, that is interpolation technique. That means we're estimating your variable of interest at a specific location or at an unknown location with the help of known locations, right? That means for each and every parameter, I'm just moving back and forth just to make people understand how actually I've achieved this result. For each parameters and for each location, right, we map, right, for the entire city using simple interpolation technique. And after that, we actually integrated all those particular layers. That means for the pH layer, we have created one pH layer. That means technically what we did is we made it one, I would say one point data to a surface data. And after that, we just integrated, and this is what is your combined result. And this is what the water quality scenario in the month of, sorry, not exactly in the month of the pre-monsoon. Actually, the data we collected actually nearly May, right, before the monsoon starts. And here you can see the red portion is completely unsuitable, and this green one is yeah, this blue one is says suitable, and in between you have this moderately suitable. How actually we have identified this? Based on certain data set. For example, you can see here the BIS standard. Based on this BIS standard, we categorize the data, and we actually process in geospatial technology, specifically in GIS environment, to get this particular thing, right? And this is for the post monsoon, and this is for pre monsoon, because of the dilution effect, right? Your number of, or the area under the, what I would say, unsuitable area drastically reduced, right? So that kind of insight actually give it to the policymakers, right? And also you try to see what exactly the currently the land use pattern in that particular area. It's a simple supervised classification of a satellite image, high resolution satellite image, where we have just identified where are the built up area, where is the vegetation, where is water bodies, right, and where are the encroachments, right? So that will give a better picture of why at a particular point your water is getting polluted. Okay, so this is just one case study through which we communicated to the policymakers that this is what is the condition. And the problem we discussed at the beginning, for example, look at this particular area, open land, these are actually two water fields. So that requires some kind of modeling, hydraulic modeling or groundwater modeling studies. So that will give you up to what extent actually we can extract the, I would say, groundwater, so that there won't be any saltwater intrusion from the sea towards landward side, right? That kind of information or insight also we gave to the policymakers. So this is just one case study. And coming to another case study, here, there is the problem here is slightly different, right? If you look at this map, right? If you look at this map, and this is close to Mumbai, and can you see the cursor here? Hopefully, you can see the cursor where I'm actually pointing, and I'm also, yeah. So this is for the Ullas Valdhuni River, right? And here the question was why a specific stretch of a river is getting polluted, right? And there are also a lot of court case and a lot of NGOs, they are also complaining against this State Pollution Control Board that they are not taking care of this particular stretch, or they are just giving free hand to the industries, right, to pollute our nearby rivers, right? So in that particular situation, what we studied is we try to visualize, okay, if there is a pollution, where and how much pollution has taken place. How do we visualize it, right? We did a very similar approach. We collected the sample data, right? We collected the sample data and you also tested the water quality parameters, right? For example, let's say here, let's start with, before taking even those parameters, you can see here. So these are some of this urban industrial clusters. You can see you have in Ambernath, you have in Ulhasnagar, in Kalyan, Dombi Valley, right? We have also industrial clusters, right? That means a lot of industries are operating from that particular region, and you keep an assumption that might be due to this particular industrial sector, your river is getting polluted, right? So then slowly and steadily, we just do a simple LULC classification just to understand where are the built up areas, right? Why a particular stretch of the river is getting polluted. So land use will give you that how a particular piece of land is being used by the people, right? And this is, and if you look at this, so this is what the parameters, right? This is the water quality parameters, like you have a BOD, you have a TDS, biological oxygen demand, you have a COD of TDS, and you have fluoride. So you can see that this particular stretch, that means towards the southern and eastern, southeastern, right, part is actually less polluted, right? It is less polluted in comparison to your north and western part. Okay, so this is the yeah, this is southeastern and this is northwestern part. You can see as the river flows towards the what I would say downstream, right? So most of your parameters you have actually very higher concentration. Even we have noticed even the pH value has also gone up to close to 2 or 3. It's almost, I would say, very concentrated acid, right? So based on this data sets, once you visualize this, you will get at least the fast and information of from where the again the challenge here was what is the source of pollution, from where it is coming, right? So what we did is we further narrowed it down to simple industrial clusters, right? So we have identified those 3, 4 there are industrial clusters, and for each and every cluster we map them, right? We map them using again this geospatial based technology to understand where are the industries at and what's the type of it and what kind of pollutants they release, right? What actually noticed here, either uh, the data we got it from this all MIDSs, we don't have any detailed information, or the data is missing, right? So the point here I want to highlight is here that that means due to this data gap, right? Even though you say that the river is getting polluted, but due to this data gaps, we are not able to confirm whether this particular source is polluting. However, from the quality parameters, you could say that whether the pollution is coming from your domestic part or it's from industrial part. So this is how we could able to convey the policymakers that what kind of further data set that you need to reach out a pinpoint source of pollutions, right? And these are the two studies where we deploy geospatial technology to understand or also convey message to the policymakers to take some kind of decision on that, right? Okay, so now coming to another aspect where I'll be talking about that what kind of questions people ask in urban floods. So now if you see, for example, floods, right? It is so nowadays people are not talking about rural floods, right? So they are talking about urban floods. Why? Because urban flood is becoming now more frequent, right? And if you just have a look at those pictures, so you see your fancy cars are actually just swimming, right? I would say, and look the city, how it looks like, right, in the rainy season. So why actually this matters is because it happens for maybe 1 or 2 or 3 days, but the kind of losses or the kind of damage, right, it brings is enormous, right? So that's the reason nowadays people are also becoming worried about the urban flooding, and see how geospatial technology can be used to actually address those particular concern. So what I think, so here this is the Chennai flood and this is Vadodara flood, and the famous Vadodara flood is that if you look at the picture which is in here, you can see the crocodiles, right? The crocodiles are swimming in the city, right? Due to this Vishwamitra river, right? Yeah, yeah. First, I'll start with we did a simple study for Hyderabad, right? And here the policy question was, can you identify the wards, right, in GHMC region, that is your Greater Hyderabad Municipal Corporation, that which are the wards which are more vulnerable to urban flooding, right? And this is what the study area is, right? And you can see there are two lakes here. We have Usman Sagar Lake and we have also Himat Sagar Lake. And these two lakes also supply drinking water to the city, not full, partial, right? And this is the called Musi River, right? So what happens here, the policy question was, how do you actually demarcate those particular wards, right? That was the policy question, so that necessary mitigation measures can be taken. So before jumping into that, to identify the wards, we need to also understand that built up area nowadays means most of our cities are getting concretized, right? And its concretizing is happening very rapidly. So our first observation, sorry, our first objective was, is it possible to quantify the percentage of built up area or the impervious area that has increased over the period of time, right? Because this is what our common understanding is, that the impervious area restricts water, right, to percolate, and as a result, we are getting more runoff that leads to flooding. And also, there are other reasons is the rainfall intensity, right? The increase in built-up area and change in the rainfall pattern, right? So these are the two, I would say, major driver of our urban flooding. And plus, there is also no proper drainage system in the city to carry the amount of the rainfall that actually generates during a specific high intensity rainfall. So our here objective was to see what is the percentage of built up area that has increased over the period of time. We are not just computing as a city, but also segregated ward wise, right? Because whatever a decision is being taken, right, it must have some administrative units, right? For example, you need to come out with the which ward is more vulnerable, so that ward specific, target specific intervention measures can be done. Yeah. Yes, this is what you can see the left side image, and here we have used actually simple Landsat images, because here our interest was only the built up area, and in the right side you can see this is the built up area for the year 2022 at the gap of 2022 years. And this is what the change in the built up area for each and every ward we estimated what is the percentage, right? So here the assumption was, if it is more built up area, you will have most likely that the area will be also flooded. Also, the condition here is you also need to look into other parameters as well that might drive the flooding part. So what also we did is, we took also other parameters, like we took the digital elevation model. That means here for ward wise, we actually did it ward wise analysis, right? Ward is nothing but it is the minimum, the administrative unit in a city, right? And we have road density, right? Road density is also one of the proxy indicator of your urban development, right? If you have more roads, the density, that means the area is more urbanized, right? And you have a slope determines what is the rate of change of elevation plus the rainfall intensity. This is actually absolute values, not intensity. So we took actually the rainfall of past 20-30 years, I think more than 30 years, using the Google Earth Engine platform, and see how the things are actually the rainfall, the magnitude of the rainfall varies in a city, right? And we simply combine these what I would say 4 layers plus this 5 layer And an HP environment, we call a simple analytical hierarchical process, and this is what the output is. So these are the words we identify that are highly vulnerable. We have very high and high, moderate and low, right? So when you have such kind of map, you can easily communicate the situation to the policymakers. So these are the words going to be impacted whenever there is a flood, right? Accordingly, necessary measures can be actually can be done to mitigate those urban flood to reduce the damage and other thing. Yeah. Okay. Yes. Uh, yeah. Am I clear and audible? Should I go ahead?
Yeah, sure, sure.
Yeah. Yeah. Thanks, Prakash. Yeah. Yes, another here, I'm going to show you that again, this is also related to urban flooding, right? It's a very similar studies, but here, because you deployed geospatial technology along with some modeling and simulation studies, you could able to tell some kind of excellent policy questions. For example, for a given amount of rainfall, right? In earlier studies, our objective was just to see which are the wards which are more vulnerable, less vulnerable, right? And in this particular study, what the policy question was, for a given amount of rainfall, how your city will be impacted, right? To address such kind of questions, right, that requires different level of analysis. So apart from the normal geospatial technology like mapping and monitoring, here you have deployed another dimension, that is the modeling dimension. So through that modeling dimension, you could actually create lot of scenarios that will answer the policy maker questions, right? I'll show you actually what we did it. So here in the Vadodara city, if you see the scenario, let's say in 31st July, I don't remember, it's in 2019, I think. Yeah, it's 2019. Yeah, just before COVID. Yeah. In just 6 hour interval, right, we are getting 500 mm of rainfall, right? And this data actually collected from the global data set. The actual data set might vary in terms of some percentage plus or minus, but this is what the estimate from the global data set. So what we did is we tried to simulate, right? You might be knowing that it is nothing but you are just mimicking the natural or urban processes, right? To try to model the flooding processes, right? What is the source? What is the speed? Other aspects. Happens is here we can get a lot of, because you had also deployed another model, right? And that will give you simulation, and that in a spatial environment. If the inundation is there, where and how much, what will be the depth of it. So what actually we try to further analyze this particular result is, because we are doing it for a city environment, and the city environment is very, very complex, and it also subject to what kind of data, what is the resolution, the other aspect of it. Whatever the data set you had, you first analyze it, and after that we see that if this is the inundated area, right? And what exactly the land use pattern, right? So that means we have one land use layer and we have one inundated layer, right? Then you just simply clip it, right? By doing so, you will get what is the percentage of built up area that would be under water, right? You can see here, this is what for a this existing scenario, so the existing situation specifically, this is we did it for the 31st July, right? And this is what the scenario, you can see the higher percentage of built up area, this is the followed by this water bodies, you have a fallow land, and this is the plantation. This is at the percentage of area that will be underwater, that was underwater for a given situation, for a given magnitude of rainfall. Now what happens is you also break this down to the percentage with respect to each and every ward, right? Why we're actually doing it ward wise analysis? Because the policymaker always look at what is the minimum administrative limit, right? What is the, which ward is getting impacted, accordingly the necessary mitigation measures can be taken, right? So here we also further analyze to word-wise manner, and later on we perform some kind of scenario-based studies, right? We perform some kind of scenario-based studies where here for example, what will happen, right? If exactly whatever the things that happen in terms of rainfall, let's say it will be doubled, or the rainfall amount will be more than 50% of what was the rainfall it was in 31st October, right? With respect to what I mean to say is, this is what the situation they face. What will happen if this particular 500 mm will be doubled, or it will increase by 25%, or it will increase by 50%, right? So such type of questions, right? You can't answer unless you deploy some more advanced methodology, right? So to address those policy questions, we also went back and simulate from multiple scenarios, right? What will happen if there is 25% increase in the rainfall, or there is a 50% increase in the rainfall, or there is the rainfall amount will be the double, right? What will happen? So here you can see the second plot. What will be the inundated areas? For example, this is what is the first bar is the our original thing, where you can see nearly 20% is inundated. If you increase by 25%, it will further increase to nearly 26%. And let's say rainfall amount is, let's increase by the 50%, right? So it will increase to 34% approximately. And if you just increase by the double, it is actually reaching 40%. That means 40% of this entire city will be inundated under the area, right? Inundated area. So that kind of policy questions can be answered if you have this geospatial technology and integrated with the other hydrological models will give you the answer, right? So that we call it a different scenario generation. That means through this different scenarios, we can see that how each and every scenario would behave, and accordingly necessary measures can be taken. So this is what the scenario is, the 25%, and this is with the 50%, and this is with the 100%, right? And this is what the overall scenario for floods, right? Accordingly, a necessary mitigation can be measured. I think this is what my last slide, Prakash. Dr. Prakash, I'm done with the presentation. If there is any questions or anything, I'll be happy to answer.
Yeah, yeah. Thank you, Dr. Deepak. So this time is open for questions now. If there are any questions or any doubts, I think the floor is open for all the participants.
And I just completed my presentation before time, keeping in mind that we can have a little more interaction, because
So can I ask?
Yes, ma'am. Please go
Yeah.
ahead and ask.
Yeah, I just wanted to know, you have worked for the water quality of various rivers and other details. So was that project under DST? How have you acquired that project?
yeah, that actually got the help of which project you're talking about, ma'am? You're talking about
You
Puri
you
City.
yeah, water quality. You had examined water quality about that Puri city.
Yeah. It was funded by Odisha Sewerage Water Supply and Sewerage Board,
Okay, okay,
and they provide us all the facilities, all the lab and other
okay,
facilities. So we had a big
okay,
team,
okay.
madam. Actually, we had a big team, and
Yeah,
this study was
yeah.
conducted with collaboration with
Mm-hmm.
National Environmental Engineering Research Institute.
Okay,
Yeah,
okay. It's interesting. Yeah. Thank you so much, sir.
thank you. Yeah.
Yeah, hello. Yeah, Deepak, Sangeeta here.
Oh, hi. Yeah.
Yeah. So I have one question. Like, as you're talking about the geospatial policy and how the things are going to change as per this policy. So, as we did a small work in like how to adapt geospatial policy in education environment. So, as you're closely working with this, what are your suggestions? Like when we are seeing towards, because there are special provisions for education and research in geospatial policy which is being drafted. So what are your suggestions how the institute should go ahead to take the advantage of this policy to the fullest, because so many faculties are here who are attending the FDP, and obviously they want to carry forward the research in this area, or they want to start some kind of education related initiatives at their institute. So if you can just throw some light on this, so that would be very useful to all of us.
Uh, Dr. Sangeeta ma'am, so you want the policy of geospatial technology in the education sector, or I just want little clarity on your question? Uh,
Yeah, how yes, in educational sector only.
Okay, okay, I got it. Yeah. So, so here, ma'am, actually, my presentation was actually related to how to integrate geospatial technology with public policy. And coming to this, we have this NEP also, madam, coming, National Education Policy, where they're actually talking about all the interdisciplinarity, right? For example, if you look at geospatial technology, it was related to only uh, students are with a background of only geo background or any other backgrounds. Now we are also, ma'am, talking about what I would say the interdisciplinary aspect of this. uh, I think in that way we can actually introduce this, right? I hope I answered your question partially, because for the educational policy I feel I may not be the right person. So here, ma'am, we are actually working on the integration of the public policy and geospatial technology. I hope I'm audible and clear.
Yeah, yes.
Yeah,
Yeah, thank you so much.
yeah.
Any other questions from the participants? Okay. So, so that means what I kind of gathered from this session is that so for any need that public faces and that problem which can be addressed by GIS, that can be converted into some policy making decision to help, because we are now dealing with spatial context. So that's what it is. Yes.
Yeah, and also I want to highlight here because some of the things I missed here, that a lot of socio-economic issues. For example, let's say now sensors, we have NFHS data, we have also all other socio-economic data sets also that requires our geospatial interventions. And this is the area which is very less explored. Because if you talk about any policy makers, they are actually from either economics background or from the sociology, and very less people are from technocrats background or technological backgrounds. That's where I see actually there are a lot of scope where people can use this for socio-economic activities, apart from all this technological image processing and other thing. Other related to all the socio-economic, like we have the data set of people are measuring the poverty, people are talking about education, violence, right, against the women, right? So these are the some of the socio-economic parameters also can be integrated in this platform, right? So that you can exploit more about the geospatial technology in other domain. Yeah, that's all from my side, Dr. Prakash. Over to you.
Yeah. Thank you. Yeah, there is one more question in the chat. Uh, Sir, I wanted to know how can the integration of GIS and medical data revolutionize risk profiling and healthcare policy making in India while addressing challenges of data privacy and accessibility?
Uh, yeah, can be done. Uh, I remember there are a couple of students here working related to maybe it is related to the malnutrition and different drivers of the malnutrition using different ML algorithms like clusterings. They're also identifying different clusters, and that clusters belongs to which of the districts, right? Yes, if I just read out the question, integration of GS and medical data will revolutionize the risk profiling and healthcare policy making in India. Oh, okay. So medical data, what exactly, what kind of medical data means? It has some locational relevance. Yeah, can be done. That all depends on, this is Reba Khan, right? That what exactly you are looking for, yeah. Fragile information, yeah. Because, yeah, only thing is what exactly your objective is, right? You are saying risk profiling, right? So what exactly you want under that, right? You want to, let's say, uh, region specific. For example, if you look at what the Eastern India, right, we are getting a lot of cancer patients, right? This is what my general understanding is, right? So in that way, you can actually profile it, right? Because anyway, whatever the data actually you have, it's related to medical data or any other data, it must have some spatial relevance. Then only you can integrate with the GIs, right? Yeah, and data privacy and accessibility. Data privacy is a big issue, I will tell you. It's a big issue. I can't comment on this. And accessibility, yeah, that can be achieved, but data privacy, it's a really debatable issues. People are saying that we are going to protect your data, which is actually is not happening. Yeah.
Okay.
Yeah.
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 Thank you. Yeah. Yeah. Thank you so much, Dr. Deepak, for this insightful presentation. Actually, we thought we will conclude, our session. We are talking about algorithms, spatial resolutions, high
Yeah.
performance computing. So, but
Yeah.
we thought that this session would, make some practical relevance to the existing scenarios, that we are not far from what we are learning. So that came out very well through this session, and we really thank you for your time here. And this is a small token of our appreciation, a virtual token, and
Yeah.
hope you would accept it.
Yeah.
And in
Thank you.
future, maybe we will have some more sessions from you.
Yeah.
Thank you so
Yeah.
much for joining.
Thank you. Thank you, Dr. Prakash, for this opportunity. Yeah. Thank you.
Yeah, thank you so much. So, yeah, for all the participants, the next session we will start at 6:30 sharp. We will have a valedictory session. We request all the participants to join in time, and so that we can also finish in time. And during this valedictory session, we will also post the quiz questions in the chat group, so that you can all fill in the quiz. You will have some time to 2 hours time where you can answer these questions, but the link only will be posted in the chat box, in this group. So, and later it will be sent through email. So please join us in time, and we'll have a break of about 45 minutes before we come back. Thank you so much.